Good morning, one and all present here. Today, although we all are suffering from the pandemic, we all know that everybody is suffering and we are not mentally very strong. But nevertheless, we are having the blessings of the Almighty with us to be safe and secure always. And with the blessings of our honorable founder president sir, Dr. Ashok K. Chauhan sir, with the blessings of honorable chancellor sir, Dr. Utul Chauhan sir, with the blessings of honorable senior VP sir, with the blessings of honorable vice president sir, with the blessings of honorable vice chancellor sir, with the blessings of respected director sir, respected registrar sir, we want to start our today's session of this technical colloquium on a topic which is an emergent topic today, a vibrant topic today called quantum computation, the requirement of that in engineering and medical sciences. I welcome you all on behalf of Amit University, Jharkhand, and to all the attendees, the dignitaries, respected Honorable Vice Chancellor Sir, all my respected colleague, and the expert today also present here. Let me give you a small glimpse of today's session.
मेरे पास आ जाओ only for ललित सर है. Sorry to interrupt you, sir.
Sir. Let me give you a small glimpse of today's entire session, that is the program flow. After starting the session, we would like to have the blessings of Honorable Vice Chancellor Sir present here with us today, along with some addressing on the topic which is very known to Sir, or rather Sir is very interested on the topic, and then we will continue with the speech of the experts, starting from Professor Dr. Siddhartha Bhattacharya. Then we will go for the speech or the address on the same topic from Mr. Utpal Chakraborty, who is basically the head of AI of Yes Bank, and then we will have a joint session from Professor Dr. Debashish De, along with Mr. Sudhindu Kumar Mandal, and the last session would be very much interesting for us because that will basically be focusing on the working rather than the theory. So with this, we all expect a very beautiful session to hear today, here with all the experts along with our Honorable Vice Chancellor Sir. Now I would like to request Honorable VC Sir to please give us the blessings and the address on the topic of today, that is quantum computation on engineering and medical sciences. Sir, if you can kindly shower your blessings and the addressing speech.
Well, very good morning, Dr. Mithun and the panelists here. I personally am extremely delighted to be part of this particular session or colloquium. There are advances which have taken place in the area of quantum computing, and they are very recent. Since research is something which generally bases its, I would say, pillars on the ground of past innovations or past laurels, but quantum computing is essentially a marriage of quantum mechanics and information technology. So there is a new field which has come up, which is quantum information technology. For those who are maybe very new to this, there are many universities which have now started this program on quantum computing as an elective, or even started teaching quantum mechanics for engineers. Now, I'm not going to be very particular about how the quantum computing is going to be utilized for engineering or medical science, because there are experts who are available and they will be able to throw light. I would possibly only throw some initial feel about the advances which have already taken place, and what are the ingredients which are important. Say any classical system was basing its whole concept of understanding a problem on the available parameters called mass, the force acting on it, and possible accelerations. Now, if the dimension was 1, it was very easy to calculate the force acting on the mass, and you know the acceleration, therefore you know everything related. Once you know the acceleration, you know how much of distance would it cover in that, how much of time, and the direction of course gets fixed if this dimension is 1. If the dimension was 2, it was broken into two components. So we call that as two-dimensional system, or X or Y. So then the force also got divided or were understood in terms of two components, which were force along x direction, force along y direction. Therefore, respectively, again, acceleration along x direction and y direction, but mass being the same, because mass is a scalar quantity. So there were components of acceleration along x or y depending on the components of force along those directions. Now this was initial. Then came the three dimensions, and then you had ax, ay, az, and fx, fy, fz. This is again classical. What happened when quantum mechanical system came? If you had fx and fy, is there a possibility of a combined state of fx and fy? Even though we say f is equivalent to fx plus fy plus fz, that is essentially a vector addition of all the three, but is there any superposition of the force between the two? Or is there any direction which is not just x and y, but at an angle which has impact of both x and y together on maybe A in general? Now this is where the quantum mechanics jumps in, or the concept of superposition jumps in. And if you understand superposition, then any complex state can be further divided into possible combinations of simple states. So any complex system therefore can be studied in terms of possible simple states, and the complex system is nothing but superposed states of all these simple states. This is the crux of the quantum mechanics. And this later is also understood in terms of you say that as a wave, or you then further go on to understand this as a field. So when there is a field along or spread along the space, the interaction between field takes place, and the whole concept of field theory has come up, and complex problems have been understood using field theory. Now, this is the simple words. I'm not using any complexities here. And once you understand that a complex system can be broken into simpler parts, simpler behavior can be understood. Therefore, the superposed impact of the simpler behavior can be treated as the behavior of the quantum mechanical system or a superposed system. This is one. Now, each system or each state is understood by the energy levels that it has, or the energy content that it has, or is explained in terms of certain quantum numbers. Now, this is where the quantum mechanics, again, numbers come. Each state is nothing but an interplay of quantum numbers or energy states, and there are so many energy states and different types of it. You have heard of a simple atom being divided into or being understood in terms of principal quantum number, azimuthal quantum number, spin quantum number, magnetic quantum number, and so on. So the energy of a state is understood in terms of the combination of these quantum numbers. Now, if there is one state, a set of quantum number is unique. Another state, another set of quantum numbers is unique again, and there can be no two state with the same quantum number set. Now, this is Pauli's exclusion principle. That means every other state is excluded from having the same state of quantum numbers as any other. So each state is a unique combination of quantum numbers. Having understood that, now when they superpose, what is happening? A new state is getting created, and a new set of quantum numbers also develop. So the wave concept allows this superposition of even energy levels, and those are understood in terms of quantum particles. Any system which describes these quantum particles is quantum mechanics. And classical mechanics fails to explain concepts which are within the realm of the quantum mechanics. So the failure of classical mechanics itself gave birth to quantum mechanics. Quantum mechanics essentially deals with particles which are of small masses, unlike the classical, and high speed, unlike the classical system again. So smaller mass and high speed means higher energy. Higher the energy, greater is the depth with which the interaction takes place, and therefore greater is the possibility of interacting or superposition. Now that's the beauty of the quantum system. That's how one has to begin with when you have to deal with the quantum system. Okay, I'm not here to teach things, but just to give you a flair of those, especially for those children, especially students who are listening or faculty members who may be interested. Then comes what? Where have we reached as on today? If I talk of some advances which have already taken place, I can let you know that the Google has already made a physical quantum system of 54 qubits. We understand bits in terms of zeros and one in classical system, but we have qubits in terms of the quantum system, wherein qubit is again superposed state of bits. That means you can have a quantum state or a qubit which has some impact of the zero state and some other impact of the one state. This is again the superposition. So 0 and 1 state combined in a manner that the probability of finding the particle in this state, of course, is 1, total probability. So it can have some probability of being in the 0 state and some other probability of being in the 1 state. Now what is this? It can be A may be the probability of say 0 state, B may be the probability of 1 state. If you combine, the only condition is A square plus B square has to be 1. And then you can have any combination of A and B. What does it mean? That means it can be A is equal to 0.1, so B will be 1 minus 0.1 square under root. So you can have so many B's. So each A will have corresponding B, and therefore so many AB combinations are possible with just 1 0 and 1 1. That makes the infinite possibilities of quantum states in qubits, and that is where information therefore can be hidden or written or understood in terms of these qubits, and a large number of qubits can be manipulated, unlike 0 and 1 which is in the classical system. So I was talking about the Google being working on this 54 bit system, 54 bit still, but those are quantum mechanical systems. So what has been done is they did a calculation which was otherwise in the classical system it would have taken almost 10,000 years to calculate. Just to throw some light on where quantum mechanics is today. Quantum computing is today. So a classical calculation on the classical system would have taken 10,000 years to calculate, and the 54-bit quantum system by quantum computer by Google has taken only 200 seconds to solve that problem. Now, if the qubits increase, please understand how fast the calculation will go on. time will reduce like anything, and most of the problem in the world will become solvable. Plus, the problem of security that we are talking about, or insecurity that we are talking about, the cryptography as a whole will result into a new, I would say, era wherein no code can ever be broken by anybody, because quantum system will have infinite possibilities of putting the codes. So that's the beauty of this. So we are in the world of quantum supremacy now. Forget about the physical supremacy or digital supremacy. Now it is quantum supremacy. A new supremacy is being talked about. China has sent a satellite, which is wherein it carried one photon and put it on the orbit of the satellite. So one photon was carried from Earth to that place, and the impact of the on the cryptographic calculations that they did was very crucial to solve n number of problems in the present physical world. Then there is a combination of the two technologies which is going to come in future, is the quantum key distribution, QKD, that is called QKD, quantum key distribution. Key is again that password you can call, or a unique thing about a system. So QKD is being combined with blockchain, and that's going to give you a transparency of highest order that you cannot imagine now. And therefore, this is a very well sought area of research for future. uh, how do we move towards this quantum superposition is a matter of understanding the quantum logics, and then allowing the quantum circuits to really break free under any potential possible under the earth, and when they interact, we are able to make measurements on the quantum scale, which is worth a research, and which is worth understanding for future as well. Then you have, sometimes it is called D-wave quantum advantage. The IBM as well as Google, both in their quantum competitions, are racing to build most effective universal quantum gate computers. You understand gates anyway. So universal gates are those which can be utilized as any gate, which is either it can be OR gate or a NOR gate or a gate, or a NAND gate, AND gate, all that. So universal gate is one which can be utilized in any way. So if you are able to develop a quantum universal gate, on which IBM and Google are two great people who are working on it, and they have a target to spend around $2 billion on this particular project. So people who are trying to become an expert in the area, or doing little thing, even 2 qubit system, if you understand now, and move to 4, there are a number of calculations that you can do which others have not done yet. So there are problems which are unsolved still in the classical regime, can be solved very quickly, and IBM and Google are thinking of having 5,000 qubits. Google has only worked with 54 so far, and they have thought about 5,000 qubits already combining, and if that system gets developed, huge research, huge new calculations with speed and accuracy is a possibility. I would not take more time. I threw some light on this. There are many major companies and startups which are coming up and teaming up and with the government, and they're moving towards this quantum supremacy, to say so. Arguably, it is the implication of the technology which is more important, and therefore the quantum supremacy will come in, and it is hoped that maybe next 10 years of time you will have all computers, not 10, I should say a little more, maybe 20 years or 25 years or 30 years, at most 50 years, most of your computers will go away, and it will all be quantum computers. It will occupy so small a space, it will be with you anytime, anywhere. So any calculation is possible just by signaling a small thing. So quantum computing can transform this R&D in every possible field, including what we are essentially trying to answer is engineering or medical field, or it can be a field of real good research. Because if the simple computers have dealt with the pharmacy and the production of so much of real required particles of the form which will help the medical science in a different way, the quantum is going to have maybe 10,000 times more speed and accuracy. So, become a quantum mechanics or quantum computer enthusiast, and remain in communication with the research world in future as well. With that, I would hand over to Dr. Mithul. Over to experts. I'll be here to listen to all of you. Please carry on.
Thank you very much, sir, for your encouraging information that we gathered from the addressing, as well as blessings that you showered on all of us to take this ahead, this research forum ahead from the Amit University, Jharkhand, on quantum computation on engineering and medical sciences. Thank you very much, sir. We are now with us our respected registrar, sir, Prabhakar Tripathi, sir. Sir, if you can kindly shower your blessings with us here today in the colloquium of the quantum computation on engineering and medical sciences. Sir, if you can kindly bless us with your words of wisdom.
Thank you, Dr. Mithul, sir.
Sir.
With the kind permission of Honorable Vice Chancellor, sir, I first of all welcome the expert on this wonderful topic. Though I am a physics graduate also, but I must appreciate that more than my teachers, I have this quantum word from my Honorable BC, sir. This is because of his very diligent work on this quantum theory there. And this is wonderful session which the students would be benefited certainly. And I don't know much about quantum because this had been a long time when I was a student, I was studying there. But certainly I should say that this smallest particle theory is going to take responsibility in giant level in future technology. So what I would expect that students should seek the opportunity in this theory. This theory really required diligent understanding, mathematical computation skill, and other skills. But once you got this in your hand, so the future would be in your hand. So once again, heartful thank to the expert, and we would love to listen in. Thank you, Dr. Mithun, sir.
Thank you, sir. Thank you very much for your words of wisdom and the blessings that you showered. Now, along with us, our experts are already present here in the panel. I would request Dr. Joyita Chattopadhyay, Madam, who is the research coordinator of the university, to kindly take ahead the session with the introduction of the speakers. Ma'am, if you can kindly.
Thank you, Mithun, sir. And now our next speaker is Dr. Siddharth Bhattacharya, sir. And I'll take opportunity to read out his brief profile here. Dr. Siddharth Bhattacharya, sir, did his bachelor's in physics and then bachelor's in optics and optoelectronics and master's in optics and optoelectronics from University of Calcutta. He completed PhD in computer science and engineering from Jadavpur University in 2008. He has been appointed as the ACM Distinguished Speaker for the tenure of 2018 to 2020. He has been inducted into the People of ACM Hall of Fame by ACM USA in 2020. He has been appointed as the IEEE Computer Society Distinguished Visitor for the tenure of 2021 to 23. He is currently serving as the principal of Rajnagar Mahavidyalaya, Rajnagar, Birbhum, West Bengal. He served as a professor in the Department of Computer Science and Engineering of Christ University, Bangalore. He served as the principal of RCC Institute of Information Technology, Kolkata during 2017 to 19. He has also served as a senior research scientist in the Faculty of Electrical Engineering and Computer Science of VSB Technical University of Ostrava, Czech Republic in 2018 and 19. Prior to this, he was the professor of Information Technology of RCC Institute of Information Technology, Kolkata. He is the associate editor of several reputed journals, including Applied Soft Computing, IEEE Access, Evolutionary Intelligence, and IET Quantum Communications. He is the editor of International Journal of Pattern Recognition Research and the founding editor-in-chief of International Journal of Hybrid Intelligence, InterScience. He has guest edited several issues with several international journals. He is serving as the series editor of Ideal Global Book Series Advances in Information Quality and Management, Deep Vetter book series Frontiers in Computational Intelligence, CRC Press book series Computational Intelligence and Applications and Quantum Machine Intelligence, Willy book series Intelligent Signal and Data Processing, Elsewhere book series Hybrid Computational Intelligence for Pattern Analysis and Understanding, and Springer tracks on human-centered computing. His research interests including hybrid intelligence, pattern recognition, multimedia data processing, and he is on the board of directors of International Institute of Engineering and Technology, Hong Kong. Welcome you, sir, and thank you for accepting our request to join this program. It will surely enhance our knowledge in this important topic. Now, I'd like to request Dr. Bhattacharya, sir, to present his slides among us. Over to sir.
I hope I'm audible to all of you.
Yes, sir.
Yes, thank you very much for your nice introduction, and also I would also like to express my gratitude to the Honorable Vice Chancellor and the Registrar and all the faculty members and organizers of this event, a much needed event rather, because you know the technology is evolving all across the world, and quantum computing has been a buzzword nowadays. People are speaking, each and everyone. If you just go outside and if you look into social media, people are looking and staring across different facets or different aspects or different events related to quantum computing. And it has been aroused a great amount of interest, hopefully. But the genuine problem is that you see, people generally think that quantum will be having a quantum desktop computer in the near future. But as far as I may be pessimistic, but I'm not so sure that whether a quantum desktop computer will come into existence, because it is not that so easy. Because the physics behind quantum computing or quantum computer has not yet evolved. It is still in its orphancy. So physicists are working day in and day out to evolve ways, and nowadays several companies, reputed concerns like IBM, Google, as Honorable Vice Chancellor pointed out, they have come with different versions of the quantum computers in their own way. We're using different technologies. Some may be using superconducting technology, some may be using photonic technology. So people are on their effort, they are using their efforts to come out. But in any way, it seems quite impossible or rather quite distant to have a quantum desktop computer as such, because the philosophy or the main aim of having a quantum computer is not to play games, video games, or do some calculations which can be done easily in a calculator or computer. So these are meant for doing some complex calculations which cannot be achieved in real time by using conventional computers. That is the main objective and main motto. So that simply applies to industrial applications, to some space applications. So those applications which require huge amount of computational power, huge amount of computational time and time complexity, that can be addressed quite easily by the quantum computer. And also, in fact, and even if you go by Moore's law, you see there is a physical limit after which you cannot go for increasing the number of components in an integrated circuit. So the miniaturization of devices ultimately gets halted after a certain time. So what next? So what next? The quantum computer is envisaged to fill up the gap or to come up with a new alternative which can address those problems to some extent. Anyway, without just elaborating on the pessimistic aspects, just to without discouraging you in any way, because you are because it is because I have been in this particular domain over the last 10 to 20 years now. So hopefully I have found some information, not because I am still learning, But yes, you are right. You are on the right track. You should learn. You should learn new technology, update yourself, because along with computational intelligence, quantum computing is going to come up in a fast way, and people will be looking forward to you. If you have skills, you will be having a great breakthrough in the external world. So, without wasting much any more time, I'd like to just start along with my formal presentation. I hope the screen is visible to you. Is it visible?
Yes, sir, visible.
Yes, sir. Yes, sir.
So just because when I was contacted by Dr. Mithun Chakraborty, he told me that it was mainly concerned with, the event is concerned with applications and the basics and all these things. So I thought that why not start with the basics itself? Because unless and until you get some interest into the basics and try to do something on your own, can do something on your own, you will not get interest into that, because the practical aspect of any technology is of paramount importance. So I'm just giving a brief introduction to quantum computing, because much has been said, and also Honorable Vice Chancellor Sir also has detailed most of this. But anyway, just to brush up the entire ideas. So you see, this lecture is all about introduction to quantum computing, where we will be just discussing about the different concepts related to quantum computer, why quantum computer is necessary, what are the advantages, disadvantages, and then moving forward, finally, to have you some idea or some hands-on, very little data, hands-on experience, how to build a quantum circuit and something like that using IBM Q platform. So let us start with this now. The layout of the agenda is today we'll be just showing you first a real IBM Q machine, how a IBM quantum machine should look like or looks like. Then why do you need a quantum computer? And then a brief introduction, and then in a differentiation between classical bits and qubits for the smallest entity of a quantum computer. And then superposition principle, normalization principle, and other properties also there, followed by some quantum gates, and then finally touching upon the IBM Q platform, having a flavor of it, how to work with that. So you see the picture, it is an image from IBM Q. It is actually copyrighted image. I must appreciate that proper permission should be taken for using these images, but it has been used for the public, it is in a public domain, that is why we have used it. So it is actually an image of a real IBM quantum computer. It looks like this. So from the picture itself, you will not be able to understand what it looks like, what the object is actually. A bunch of wires, a bunch of electrodes, and all these things. So nothing of the sort you are familiar with as a quantum computer. So the casing is not present. So you see, you just go back, because some of us over here, when we started our career way back, in fact, it will be quite proper for Professor rather the Honorable Vice Chancellor in their times. We used to have a huge room to accommodate a computer. So a huge room was there, and where different diodes were there and all these things. So big components. And you have to give the data in the form of punch cards, and then you have to take the output the next day. So it was something like that. And then finally, as time evolved and as different innovations came into being, it got miniaturized, and then we came up with these small versions of desktop, laptops, even the smartphones and all these things. But then the similar things also happen over here. You see the initial stage, it is a huge structure, actual structure of different electronic devices, photonic devices, and some communication channels and all these things. But the difference between the present computers in the previous years, which used to take a huge room, and with this one, which is also taking a huge space, rather, this entire structure, is that in the case of computers, conventional computers, everything is based on electric currents or electrons. Okay, at that particular level, where the change of the state or the change of the voltages imply either a 0 or 1. That is either a 0 bit or a 1 bit. That is fine. But then in this case particularly, you see the things are quite different, because here you are dealing with the quantum mechanical properties of atoms. That means the atoms or the electrons spin up or spin down, or the behavior of the ions, or if you just go for a photonic structure, the behavior of the photons. So all these things are relevant in this particular form of computers. So things are quite different because the manipulation of these electrons, the ions, or the photons in their minuscule nature is very, very difficult, because you have to, first of all, there are several conditions, several constraints need to be satisfied. First of all, you have to have an isolated environment. That means the environment should not get disturbed or perturbed by the outside environment. So you have to have a very closed and isolated environment. Second one, it should be a very stable environment. Stable means because you are only dealing with manipulating the ions and electrons. So any disturbance, any noise creeping in from the outside world, will totally shatter the structure or the stability of the system. And the third one is that you have to maintain a very low temperature, as low as that of the liquid nitrogen. So in some cases, rather. So you see, these things are very, very difficult to realize in practice, not to speak of a desktop quantum computer. So you cannot have a desktop quantum computer, a quantum computer as such, in your room, which is maintaining all these properties, having a very low temperature, having a stable situation, very isolated from the surroundings. Quite difficult. So that's why I'm not so optimistic about the existence or the revolution or coming up with a realizable, practical desktop quantum computer, even in the distant future. So you see, this is some sort of structure. As we progress, we'll be discussing how this thing actually works. What is the philosophy behind this? So you see, first of all, let us see why do you need a quantum computer? If you just go back to 1965, Gordon Moore, the co-founder of Intel, he forecasted that the number of components on an integrated circuit would double every year. Fine. But it was seen that in 1975, the number actually reached an astonishing number of 65,000, much more than Gordon Moore predicted. So what this actually forced him to revise the prediction, which ultimately came to be known as Moore's law. And it states that the number of transistors on a microchip doubles about every 2 years, though the cost of computers is halved. So if you take that into account, you see that it is actually predicted that around 2020, that is the previous year, computers should reach the physical limit. That means beyond that you cannot have the further level of miniaturization. So that is the physical limit which can be attained in a conventional computer, as far as the number of components are concerned. So, and also, whenever you go for fusing or just embedding or sandwiching more and more components, several problems arise, like high temperature, heat dissipation, all these things, heat problems and noise problems, all these things come in a connection problem. So even in the hardware phase, it is quite difficult to maintain or guarantee that this system, a miniaturized system, is going to function properly. So that is the ultimate bottleneck, because you cannot go beyond that. So if you just look at the figures over here, I am going to just increase you just see. You see, in the 1965, it was the prediction was 46. It came out to be 65,000. In 2006, you see the number still went on increasing, and 2016, it was in different cases, it was about this huge figure of components which can be fused in together. Okay, but then the problem is that after that, what next? What next? Because you cannot go beyond that. That is the ultimate limit which can be achieved in different architectures. And then that means you must have some alternative. That means quantum computer can be a boon in this regard. It can come out with an answer to the question when Moore's law fails. That means when you cannot go on increasing anymore, you have to resort to some other new technology. And that is also the need of the hour, because necessity is the mother of invention. Whenever you find that you are failing somewhere, new technology always pops up. So here, quantum computers can help you to come out of the situation in some way or other. Not necessarily to help you do some calculations on Excel sheet or do some addition of 2 numbers or write a C program. That is not the objective. Objective is you see some very high complex computations which are required, which cannot be achieved in real time. So that is the way you can think that quantum computers may be the answer. Now, before moving forward with the details, the technical details, we just have an introduction how this concept came into being. It was first proposed in 1981 by Nobel laureate Richard Feynman. Because he showed that or observed that classical computers cannot simulate the evolution of quantum systems in an efficient way. That is why he proposed a basic model of the quantum computer that can handle those situations. Okay. And also predicted that a quantum computer can exponentially outpace classical computer. That means they are so time efficient and robust that they can outpace the classical computers, outperform the classical computers in an exponential manner. And following that, 1994, Peter Shor came up with a factorization algorithm that is referred to as the Shor's algorithm, which is exponentially faster than any classical algorithm on the classical machine. That means any factorization algorithm, any highly efficient or time efficient factorial algorithm, even beyond that, it can perform exponentially faster than the best algorithm in practice. So that is another issue. Now you see, I may be wrong, but then I think that the implementation and the evolution of quantum computing has received a setback. Maybe due to one of these factors. Maybe this may be one of the factors, because you see this. If you note the last line, theoretically, Shor's algorithm is capable of breaking many of the crypto systems used today. That is, all the cryptographic algorithms or security, all these things can be easily broken. You can always nullify all those things. That means that is one concern for any nation and any policymaker, whether you are going to adopt this system or not. So that will also be a setback to the evolution, to the much needed expected evolution rate of quantum computing, because of fear psychosis. Anyway, then furthermore, 1996, Grover, he invented a searching algorithm, database searching algorithm, that was also very faster and seemed to have, was found to be 4 times faster than any standard searching algorithm, which we generally use. And as far as the evolution of the different stepping stones in the building of a real quantum computer, as they claim, in 1998, it was a 2-bit quantum computer was built. 20 years later, 2017, only around 4 years back, IBM presented the first usable computer, and then came out the race of quantum computers. They just started the race, and now each and every company is everywhere. Honeywell, every companies are coming up each and every day with new versions of it, and they're claiming quantum supremacy. And finally, it is the latest news as of now, 29 September 2020, last year. A commercial 5,000 plus qubit machine was announced by D-Wave. But the main problem remains, whatever you do, the problem regarding noise, problem regarding stability, problem regarding isolation is still a genuine challenge. And that's why the progress of having a real quantum computer is being impeded. So they claim to have a 5,000 plus qubit, but no one knows. No one has verified that. Anyway, without going into such sort of conflicting opinions, let us move forward. Now see, all of you know what is the classical bit. So it can represent 2 numbers. With a 1 bit, you can represent 2 numbers, 0 and 1, either on or off. If you take 2 bits, we can represent 4 numbers, quite simple. But you see, at any point of time, you can have only one value. Rather, that means what I mean to say, for example, you are taking a 1 bit, you can have either a 1 or a 0, not both together, isn't it? So that is the problem. Either you have the state or the value of that particular bit to be 0 or 1. Not that it is having both the values together at any point of time. So that is one situation, and you have never thought that it could be possible somehow. And what would have been there if this combination would have been possible, and what advantages it would make. So just see what advantages it can make. Now come to the quantum bit or qubit, or sometimes referred to as qubit. Sorry, let me show you. This qubit, only qubit. So what it is, you see, it is quite different from the conventional bit which we were discussing just now. The term was coined by Benjamin Schumacher in 1995. So it can exist in both the states. It is different, not the different value. These are the states, 0 state and the 1 state. And this notation, a pipeline followed by a bracket, not a bracket, this particular greater than symbol, and the value between, this is referred to as a Kate notation in Hilbert space. Another notation is there, also referred to as the bra notation. So taken together, it is the tension notation. You can have the bracket notation. So this can be either used in the represented in a bra notation or the Kate notation. So actually speaking, when you are defining a qubit or that if you just read the line, it should be read like this: a qubit, unless measured, just think carefully. There are several things over here. A qubit, unless measured, can exist in both the states, K0 and K1. Now, what is K0 and what is K1? These are the two states. If you just recollect Schrodinger's inequality principle or duality theorem, so a particle can exhibit itself as a wave and vis-a-vis as a particle. So each and everything can exhibit itself or manifest itself as a particle or a wave. So wave particle duality is there. So this K0 or K1 is actually a wave function. Actually a wave. If you think of a wave, it is actually a wave. Or it can also be thought of as a value or a particle value. So in either ways, it is actually a combination. That is, a qubit generally exists in a combination of K0 state and K1 state. Unless it is measured, be very careful. Unless it is measured. Why? Let me give you a small example. Let us suppose that you have, just listen to me. Let us suppose that you have a mobile, a remote, and any other another box of the same size of a remote. So these three devices, three objects are there with you, and you are in a room, in your classroom, say, and you are having a black cloth. So what you do, you just cover all the objects, three objects together by the black cloth. Now you just invite your classmates one by one to come into the room and predict what is there inside the under the black cloth. So, but given the fact that the people or the classmates know that the range of objects would be mobile, remote, and another box. So the values may be between either of these. So what will happen? Until and unless you remove the cloth, each and every one will come up with different guesses. That means one will say mobile, another will say a remote, another will say a box. So no one will be, actually what I mean to say is that you have covered all the three objects and then you segregate them separately and separately covered with separate cloth objects. And you let them know that these three objects comprise of a mobile, a remote, and a box. But you do not make them know that which one is what. So in either case, whenever the classmates are coming in, they will be guessing differently and random guesses will come in. But once you remove the black cloth, then only in either of the case, then only they will come to know what is that inside what was that under the black cloth. That means until and unless you measure, it can exist in any of the states or a combination of any of the states. Okay. And once you measure it, you get only one single value. That is the principle over there. A qubit also, unless it is measured by using some measurement operation, it can exist in a superposition or combination of two states, K0 and K1, for a single qubit system. Obviously, for a single qubit system, I'm telling you. So until unless once you measure it, it will either give you a 0 value or a 1 value. Now I'll be coming back why this measurement is at all necessary. And now let us move on. It is also referred to as the computational basis states. So if you take two qubits, it will be in 4 states. So here it is a single qubit, you have a 0 and 1. If you have 2 qubits, it will be K00, K01, K10, K11. 4 states will be there. So similarly, for an n qubit system, you'll be having n superposition states. But the beauty is that all these states, all these possible states are existing concurrently or simultaneously together in superposition until and unless you measure them. Until and unless you measure them. So that is what is the advantage you are getting? Advantage is that it is offering you a scope of manipulating multiple values or multiple states simultaneously, which is quite impossible or not possible in the case of classical logic or classical computers, where you have either a 0 or 1. You cannot have a combination or both 0 and 1 cannot exist together. Either a 0 or 1. You know it before, and it is binary logic rather. But here, all the states can be there with different probabilities. And once you measure it, you will get one single value. But before you measure that, all the states are equally there with different probabilities together. And that offering an opportunity for all of you, or for all of us, to manipulate them in parallel. Some sort of parallelism can be imposed over here. You can have some parallel computation, so making it faster. And also, depending on the probabilities, you can do some manipulations to get the best result out in the least time possible. Anyway, so you see, if you just represent a qubit on an IBM Q system, it will look like something like this. I'll be also showing you this afterwards. So you see, it is a 4-qubit system. There will be 16 states. So this is 1 qubit, this is another 1 qubit. So these are the different amplitudes of this particular measurement probabilities of this 2 qubit. Okay, so all the qubits here are seen to having the same amplitude that existing together in the system. So you have a system, quantum system, a 4-qubit quantum system, where all these different states are together, are present together. You do not know which state is going to be the output unless you measure it. And if you just represent them in a sphere, block sphere, it is referred to as a block sphere or Q sphere. So actually, it's a vectors oriented in different directions. So depending on some phase angle and some azimuth, I'll be just discussing that later on. But this is a snapshot of the IBM Q system using a 4-qubit quantum system. Now, as far as the representation is concerned, I already told you that it is using the Kate notation, or the Dirac notation, Kate notation, and it is in a Hilbert space. And Hilbert, what is the peculiarity of Hilbert space? Peculiarity of Hilbert space is that there is an inner product over there, which when performed between two vectors will give you a scalar, which is not possible in any other random vector space. It is a beauty that if you just apply this inner product between two vectors, you will get a scalar out. Okay, and this operation is quite useful in quantum mechanical operations. We'll be discussing that later on. And if you just think of this, a qubit now can be represented orthogonal vector. So obviously orthogonal, why orthogonal? Because if you just go back, if you just look, if you would have only two qubits, rather two states over there, so they will be orthonormal to each other, orthogonal to each other. So that is why they can be represented as orthogonal vectors. Zero state or Kate0 can be represented as a column vector 1, 0, and Kate1 as a 0, 1. Okay, and the zero state is referred to as ground state. If you just take the analogy with the electron spin and all these things, which we were discussing initially, so the ground state is the 0 state, and the excited state of the electron is the 1 state. So you are just thinking in terms of the physical physics, in terms of the electrons, either the ground state or the excited state. Okay, now come to the basic features, or the very important features. I am just discussing only two. One is superposition. I told you because also Honorable Vice Chancellor sir also told this thing before. So I told you that the number of states, a number of possible states can exist in superposition or combination, linear combination rather. Okay, so that is the superposition property, which is quite useful because that only allows you to have multiple number of states or more than one number of states together in a quantum system. Okay, depending on some probability. Another property is the entanglement. Very, very, very useful property. Although people are not so much aware of this entanglement, and very few work has been done. Most of the work has been done in the physics level. That means all the physicists that have done this. But proper implementation of entanglement is still a problem. So actually, it is a property which generally gives rise to non-local interaction among bipartite correlated states. Very, very difficult to appreciate from this line. It will be quite clear if you go for an example. I'll be giving you just an example later on. That means what it implies that you have two states which are entangled. That means these two states are somehow correlated with each other. That means if the state of one particular state changes, the value of one particular state changes, the value of another state also automatically changes, simultaneously changes. So how it happens, we'll be discussing with an example. And then you come to the superposition. Let us describe it in some form. Superposition, I told you, it can exist as a qubit, can exist linear combination of states called superposition. So in terms of superposition, you see, you can write a state, a qubit as a psi. Kate psi is equal to alpha Kate0 plus beta Kate1. So this psi is actually a wave function. It is actually a combination of alpha times Kate0 plus beta times Kate1. Where the alpha and beta are the probability and complex numbers actually, and alpha square and beta square are the probability amplitudes of these Kate0 and Kate1. That means the probability of finding psi in state 0 when you are measuring it, mind you. When you are measuring the system, I told you that until and unless you measure it, it will remain in this particular form. But once you measure it, you will get one single value, either a 0 or a 1. So the probability of getting a 0 out of measurement is alpha square, and probability of getting 1 is beta square. So whichever is larger, you will get that particular value. If alpha square is greater than beta square, you will get 0. If beta square is greater than alpha square, you will get 1. Clear? So now, if you just represent the superposition in the case of in the IBM Q system, you will see nothing like this. You see, this is a two qubits. Sorry, 2 states, 0 state and 1 state, one single qubit system, where 0, K 0 and K 1. These are having same probability. Okay. So same probability means then the vector is represented something like this. It is a vector, the qubit is a vector, a unit vector, which is being aligned in this particular direction, say. Okay. So these are actually having similar, that means probability, that means about 0.5, 0.5, say. Now, if you just have, even now you do not understand or do not have appreciated what is superposition, Schrodinger just came up with this thought experiment, Schrodinger's cat, very, very, very interesting one. You just think that there is a box and a cat is there, which is placed in the box. And inside the box, there is a radioactive source, a flask of poison, and a Geiger counter. So there are several components in the box, and the box is covered, somehow covered. You do not know what is there inside. From the outside, it is not seen. It is like something like a black box. Okay. So there is a cat inside, a living object. A radioactive source is there, which is decaying, which is radiating. May or may not radiate. May or may not radiate, depending on probability, because radioactivity is a probabilistic phenomenon. But a radioactive source is there, and a flask of poison is there, and a Geiger counter to measure the decay of the radioactive source. Now you see, obviously radioactive, we have already learned the half-life and all these things in radioactivity. So if the radioactive source decays, it is a mechanical system attached with that. That means the Geiger counter will give some reading, and that will ultimately drive a mechanical system which will break the flask. And as soon as the flask is broken, the poison will come out and the cat will drink the poison and the cat will die. However, if you just think otherwise, if at all the source does not emit radiation, what will happen? The Geiger counter will not change. There will be no manipulation of the mechanical system. The flask will remain intact. So the cat is alive. Both the cases, the cat is dead and the cat is alive. When they are happening, I have already discussed it. Now you see the beauty. Because I told you radioactivity is a probabilistic quantum phenomenon. May or may not decay and give up radiation. So you do not know that whether the radioactive source has decayed, that means whether the flask has been broken and whether the cat is dead. Until and unless you open the box and measure it or see it, measure means see it or observe it, you do not know whether the cat inside is either dead or alive. So at any point of time, there is equal probability that the cat is both alive and dead. Until unless you open the box, because until unless you open the box, you do not know what is inside happening. Because you do not know whether the radioactive source is decaying or not, or the cat has drank the medicine, flask of poison or not, or whether the flask has not broken, whether the cat is alive, but you have to assume that at any point of time, the cat inside is either dead or alive or both together. That is very, very interesting in nature. Once you measure it, once you open the box, you can see what is inside there, what is the state inside, whether the cat is alive or dead. So if you just represent that entire observation in the form of a quantum mechanical notation, you will find something like this. This is the picture. Where is the Geiger counter? There is a mechanical system. It will be a hammer. You will just come down and break the flask having potassium cyanide, say for example, and the cat, if it drinks, it will be dead. If it does not drink, or if the flask does not break, it will be alive. So the entire system can be represented by this quantum mechanical notation. Something like this, you see. 1 by root 2, this is a probability alpha, say. This is 1. 1 means say alive, plus 1 by root 2 dead. So until and unless this is the system, this is the equation, or this is the expression which is describing the state of the cat inside the system, it is in the system. So in a quantum mechanical system, all the states can eventually exist or together with some probability amplitude. until and unless you measure it. Once you measure it, you will get either these output or these output. That means either you get the cat dead or the cat alive. So this is the property of superposition, which enables multiple states to be combined together, and you can operate or manipulate the states independently, so that you can get the best possible output in the real time or in a lower time frame, depending on the probability. Now, normalization principle, you see, this is quite obvious because you see the sum of the probabilities of any event should be always equal to 1. So that is why alpha square plus beta square will be always equal to 1. So this is the constraint, always referred to as the unitarity condition. That means in any quantum mechanical system, the square of the alpha and the square of the beta of the different probability amplitudes, summation of the different probability amplitudes should be equal to always 1. This is for a single qubit system. If that is a multiple qubit system, it will be alpha square plus beta square plus gamma square plus delta square, something like that. So you see, previously, if you just go back, alpha was here a scalar, but here alpha is in a Kate notation, Kate alpha and Kate beta. So actually speaking, without losing generality, alpha and beta can themselves represent the 0 state and the 1 state as a state, as a quantum qubit state or a quantum wave function. The alpha itself is actually the amplitude itself. They can represent the 0 state or the 1 state like this. So this condition has to be satisfied in any quantum mechanical system, because the sum of the probability should be always equal to 1. Now, when you measure it, obviously, either beta comes up to be, that is beta square comes up to be 1, alpha square comes up to be 0, or beta square comes up to be 0, alpha square comes up to be 1, giving out either 1 or 0, respectively. And the Bloch's pair, how the Bloch's pair is quite simple, because if you can represent the qubit in this form, you can also represent it there using some e to the power I phi term. You can just use it because alpha and beta are complex numbers. You can always write a complex number in this form by taking out the real parts, alpha and beta, and just multiplying that with e to the power I phi, the complex part. So you can write like this: alpha psi is equal to alpha Kate 0 plus e to the power I phi beta Kate 1. And since you know that the sum of the probabilities squares will be equal to 1, so by using some trigonometric manipulation, you can write alpha is equal to cos theta by 2 and beta is equal to sin theta by 2, and hence the wave function of the qubit can be represented as cos theta by 2, Kate 0 plus e to the power I phi sin theta by 2, 1. Now it can be interpreted like this: theta and phi the spherical coordinates. R is equal to 1, the value of the radius is equal to 1. Since we are assuming that the magnitude of the qubit state is equal to 1, that is a unit qubit, and that means you can plot the qubit state on a surface of a sphere as a vector. So it can be represented like this. You see, a qubit can be a qubit. This is a qubit. This is the Kate 0 axis. This is the Kate 1 axis, and this is the xy plane. So you can represent the qubit psi as a vector having an angle theta with the Kate 0 axis, and the azimuth is given by the phi. Okay. So now there are several observations over here, because if that is so, because it is quite random in nature, isn't it? So how do you have some feasible output out of a random system? So several operations are there, like rotation, everything are there, which tends to rather rotate this qubit either in this direction or in this direction. That means they're manipulating theta. So these are several of the ones. That means if you want to have a stable system, either this should be a Kate 0 or Kate 1. So there are several operations. I'm giving one simple example of rotation operations, which can move or manipulate this to move it over here and or to here, depending on the situation. And that means there is a possibility that you will get the best possible solution out of the random solution in least possible time. Now, very interesting one. It will be quite clearer, and it will be quite, I hope that it will be quite useful for you, because whenever I give this introduction of quantum computing, in any of my classes also, I also give this example of entanglement by means of a real life example or a story rather. You see, we are presenting a short story. Say once upon a time, Alice and Bob, you know these two characters, Alice and Bob, quite famous in cryptography. Alice and Bob lived in Australia. They are growing up in their respective hometowns. Say Alice was living in or brought up in Sydney, and say Bob was in Canberra, something like that, Melbourne. Say. So they're different hometowns, but they do not know each other. They are growing up independently of each other. Fine. Suddenly it happened that Bob met Alice and they fell in love with each other. Fine. It happened, no issue. Subsequently, they got married to each other. Quite obvious, and they were living happily. So you see, two entities are at different locations. Now they came together, they fell in love, they got married, and finally Alice got pregnant by nature's law. So after a few months, Bob had to move to USA. So Bob is flying back to USA for his job, leaving Alice behind. So the entities were differently located. They came together, they combined together. They are expecting a end output in the form of a child, because Alice has got pregnant, and then suddenly one of the entities has to move out of the system. Now you just think of this story being happening in those times where there was no formal communication. That means there was no mobile phone, there was no internet, nothing like that. So only some sort of snail mail was there, some postcard, inland letters in previous times, which used to take couple of months to reach from one end to another end. Just think of this situation. So Bob has moved with Alice being pregnant. Alice has not delivered. Now see, days pass by. After a gap of several months, Alice gave birth to a child. Just think of this moment. Alice giving birth to a child means state of Alice changes from a non-mother to a mother. Prior to this moment, Alice was not a mother. She was pregnant. But once she gave birth to a child, she became a mother. That means her state changes from the non-mother to mother. Now, even if there is no formal communication of this particular news to Bob, just think carefully, logically. Bob doesn't know what is happening in Australia. But the moment Alice gave birth to the child, Bob automatically becomes a father, even if he does not know, isn't it? Because the state of Bob has changed. Bob cannot claim that he is not a father. Because his status changed, he has become a father, even without knowing that Alice has delivered. That is the beauty. You see that first the communication, you just think of the communication as such. The faster communication of the state changes, that once the state changes at one location, the state of other qubit changes at other location automatically, without having any sort of formal communication, the lightning speed of communication. So the state of Bob automatically changes, even though Bob does not know that Alice has delivered. Now, if you just put an analogy with quantum entanglement, this entanglement states that when the state of one of the entangled state changes, when the state of one of the entangled state changes, the state of the other state automatically changes. So you do not have to make the measurement at both the locations. If you measure one of the states at one location, the measurement of the other state automatically happens. So here you see, when Alice and Bob got married, they got entangled. They become an entangled pair. So that is what we refer to as mental adjustment or something like that. That is some sort of entanglement. Mental communication is there. So when the state of Alice changes to a mother, automatically the state of Bob changes to a father. So that is the beauty. That is very fast communication, fast form of transmission of information, which is quite impossible in conventional world. So this thing, people are working quite tediously on this particular topic. Although few practical realizations have been done. And also, quantum internet is coming up at a rapid pace, and this quantum internet is using this principle of quantum entanglement for the information or transmission of information from one place to another. Now, finally comes the fact of this quantum measure. Why do you need quantum measurement? So you see, all these things we are describing over here seem to be abstract, because these are all random systems, quantum systems, which cannot be visualized in practice. Now, for the common man, for us, we generally believe in some absolute numbers. 1, 0, 2, 3, 4. Absolute numbers are classical numbers. We do not know what is quantum, because if you are given a qubit, you will not be able to understand what is the value inside. Because you can only understand, because the human being from the birth, they have been taught how to understand numbers, value of number. That is 2 is greater than 1, 3 is greater than 2, and something like that. They will not understand K0 or K1, K2, etc. So whatever you do, that means even if you use the system, quantum computer, what you have to do, you have to just encode the classical information initially and feed it into the quantum computer in the quantum form. Because quantum systems cannot take classical inputs. You have to encode them somehow or transform them to the quantum domain and feed into the quantum system or quantum computer. And a quantum computer will just operate on those quantum inputs in its own way, and then deliver some outputs, quantum outputs. Now again, if you want to appreciate the result, obviously that quantum output has again to be transformed back to the classical domain. So that is why measurement is required. Where quantum measurement destroys the superposition, destroys the coherence of the two states, and so you come out with a absolute value in the form of a classical value. So I'm not going into these things. These are quite obvious physics. But the beauty is that you see that if you just think of this, because it seems quite easy because they go and just measure the system. It is not always so, because if you just think, if you just go to the first line, if one prepares a quantum system in the laboratory, the position and energy of the constituent states are measured. Obviously, you are measuring what? You are measuring the qubit states. Fine. So after measurement, the state of a system is said to collapse. I told you it will destroy the superposition, and the superposition never exists, and you will come out with one single value, depending on the probability. Okay. Now, if the measurement, very interesting, the measurement is repeated. If the measurement is repeated without allowing the quantum state to further evolve, mind you, you are repeating the same measurement after some time, say, without disturbing, without having the quantum system disturbed or perturbed or changed, it will always give the same result. Fine. But, you know, I told you initially it is quite challenging to maintain the isolation, maintain the stability, maintain the low temperature conditions, all these things. So obviously some noise will creep in. That is the main problem with any quantum computing system. So if the preparation, now once the noise creep in, the preparation gets disturbed, then the preparation is now changed, new quantum system has come up. And if you go for measurement, you will get a different value. So that is the main problem here. So don't you think, or never think of adding 2 and 2 in a quantum system. Even it may come up not with a 4, it may be coming up with a value of 5. If you are going to add two numbers, 2 plus 2 in a quantum computer, you are most likely to have a value 10, 20, different numbers, different values, different time, given the state of the art. So what you do, but if you ensure that the system remains stable and isolated from the environment, you are always likely to come up with the same result each and every time. Now, if you come across different results at different time, given the different conditions being not maintained properly, so what you have to do, you have to take an average or go for the expectation value of the entire number of observations, and then you come out with some of the value, which is actually an average of the entire values, expected values. So actually speaking, it can be appreciated that the systems are not coming up in so expected rapid pace, given the fact that this noise factor is a very, very challenging problem in quantum mechanical systems. Now, just finally coming up with some quantum gates, because we also learned from the Honorable Vice Chancellor sir regarding quantum gates. Similar to any classical system, we'll be having some quantum gates also over here. So these are unitary operator. What is an unitary operator? The adjoint is equal to the inverse. If you take the adjoint of the operator and the inverse of the operator, they are both same to each other, equal to each other. So the beauty is, if you multiply them together, you will get an identity matrix. So based on this property, you have different gates, poly gates, X gate, poly X gate, Y and Z, several gates are there. So the structure these are matrices actually. The matrix, because everything is in the form of a matrix operation, vector operation inside a quantum mechanical system. So X gate looks like this. So what actually X gate does, if you apply this X gate on a state, this is the 0 state, gate 0. So you will get the gate 1. So what is actually, it switches the amplitude of the states vis-a-vis, they swaps it, the amplitude. So if you apply the X gate on a 0 state, you will get 1 state. If you apply it on a 1 state, you will get a 0 state. So this is a typical operation. Similarly, you have the Y gate and the Z polymatrices, something of this form. And finally, this is quite important and very important, Hadamard gate, H gate. It is a fundamental gate because it allows to create a superposition. How to create a superposition of 2 qubits or 2 states rather. So 0 and 1. So you can, if you use this form of matrix, Hadamard gate, you will get a superposed state of 2 qubits. So finally, because I maybe have some time now, so I'll be just showing you how to just log in and creating an account in IBM Cube, and then see how a qubit performs, how to use the different gates altogether, come out with some simple circuitry. So let us move forward. Is the screen visible?
Yes, sir. It's visible.
I have just put that URL over there, and you will come across this page. Where you can create an account and that particular similar type of verification from the email and all these things. Similar to all the verifications will take place, and you will be your user ID will be verified and all these things. And I've already created an account over here. You can sign it over here. You can click over here, and you can sign over here. You see that the interface is coming up. So different jobs already running. Okay. So here you can get all these things, recent updates on all these things over here, recent notifications, all these things are there. So what you do just to start, for the sake of just the introduction, you just click over this icon and quantum composer, the circuit composer is there. You click over here. You see this interface is coming up. Similar figures that I have already shown you in the slide. So this is the blocks pair where you have a single, this particular vector like this. So it is a single qubit system. One single qubit Q is already there. Okay. And it is a classical channel where you have to have the measurement. So what you do, if you just now you see, if you just put a measurement channel over here, this is measurement. You just drag it over here. You see, this zero state K0 is having the probability 100%. It is the maximum. That is why it is aligned in this direction. I told you this is the zero axis, K0 axis. So it is aligned along the K0 axis, and the one state is having probability 0%. So entire value or the entire importance is on the state 0. Now, if you delete it, for example, if you just go back and then delete it and then go and can put a Hadamard gate over here. Now, once you put a Hadamard gate, what actually happens, you see, the state, I told you Hadamard gate is going to create a superposition of two states. So what it is doing, it is splitting the state into two equal parts, that is with equal probability rather. State 0 having probability 50% and state 1 having a probability 50%. So you are having both the states in both the directions with equal probability. So here by different gates also there. If you just delete this, for example, now you are able to see 0 is having the 100% probability. This is a NOT gate. If you put over here, you see the NOT gate means you are getting the 1 having the 100% probability and 0 having 0% probability. You are just reversing the steps. Okay. So several gates are there. I request you to go here and several also. Not only that, you also have a manual on QSkit, and the people are working just in like anything on this particular platform. So also because one of our speakers over here, Devash is there, Suvendu is there. They are also working very good on this particular direction using this platform. Very interesting. I'm not going into details, only for the sake of understanding. I am putting it over here. So I hope that this small introduction, I suppose it has come out to your, it will come to your use, and I am open to any question from you, and please put it.
I request the attendees, if they have any question, they can put it in the chat box or in the question answer box. We can take the questions from the attendees. Or else we can give the opportunity to the attendees to send the questions to us, and later on we can send the same forward the questions to Dr. Siddhartha Bhattacharya sir for his whatever solutions that he is providing. So thank you very much, sir, for your enlightening speech.
There is a question there.
Yes.
Mithun sir, few questions are there in the chat box.
I got it.
How can quantum computing help in saving lives during COVID-19? Very, very important question. Suppose we have to put two different altogether, but quantum computing is not going to save anyone from anything. It is only a computing platform where you can take the advantage of high-speed computation or some other computation to come up with solutions. Obviously, very pertinent question, because quantum computing of late is now being used for drug discovery. So in drug discovery, you have to manipulate the molecules, the chain of molecules, how they will combine, and all these things. So the multiple combinations are possible. So it is quite difficult and to analyze that in a conventional computer. So it may happen that the drug design will take a huge leap forward with the advent of quantum computing.
So there is one more question. It's saying asked by Akshay, saying that can you
recommend any
recommend?
book to learn? Yes, very good.
Yeah, yeah,
One
yeah.
book is one book is there, McMahon, David McMahon, and also Chuang. One book by Chuang is there. Several books are coming up. You can always take. You just search David McMahon. I would prefer David McMahon because my professors used to tell me about the Chuang, but I didn't find it so interesting. I found David McMahon to be interesting enough because it just deals with several example problems and tries to solve the problems, and also the examples are there, answers are there, and exercise questions are there. Very good approach. Anyway, you can follow either of them. And some books are also there. They're in the reference perhaps in the slide. You will see some references over there, some pointers to some books.
I would request Joita madam to please, madam, if you can unmute Joita madam.
Yes, sir.
Ma'am, if you can please take over.
Okay. Thank you, sir. And now I'd like to request Dr. Dhananjay, sir, to introduce the next speaker to the house.
Thank you, ma'am. So our next speaker is Mr. Utpal Chakravarti, sir. So he is an eminent data scientist, AI researcher, strategist, and thought leader with more than 2 decades of industry experience, including as a principal architect in different MNCs like Larsen, Stubro, Info, IBM, Capgemini. At the moment, he is head of artificial intelligence at Yes Bank. Utpal is a well-known speaker and author on artificial intelligence, Internet of Things, as well as Agile and Lean, and has spoken at conferences around the world. His recent research paper on machine learning, titled Layered Approximation for Deep Neural Networks, and his few books, including Artificial Intelligence for All and Artificial Intelligence and Fourth Industrial Revolution, has been widely appreciated at several conferences, institutions, and universities. He has also demonstrated a few out-of-the-box hybridized Agile and Lean implementation in different industries. So I would request Mr. Utpal Chakravarti, sir, to kindly share his expertise with us. Utpal, sir?
Thank you. Can you hear me?
Yeah, sir. Please go ahead, sir.
Okay. Thank you so much. So first of all, thank you, everybody. Thank you so much for inviting me for this event. And definitely it's a weekday, but yeah, still I love to hear the previous speaker speaking about different concepts of quantum. So I've got a small presentation. So normally I present it into different conferences. So I would like to share that presentation. So can I share it?
Yes, sir. Please go ahead, sir.
Yeah. So I don't know where it is. Let me just.
Sir, there is a share screen option.
Yeah,
below,
I can see that.
Toolbar. Yes.
I can see that, but I cannot see my PPT here. One second. Let me check if I can. Okay, so let me share my desktop itself so that, and I can share my PPT. Is it visible?
Yes, sir. It's visible.
Okay, thank you. Thank you so much. So I'll talk mostly, I'm not going into the concepts or the technical things of quantum computing. So mainly my area of expertise or what I'm doing right now is mainly the QML part, the quantum ML part. And I'll mostly talk about the industry, about banking and finance, how banking and finance is basically adopting quantum slowly, very slow. Now only Microsoft has started building small quantum COEs into some of the premier banks in India. Of course, in other, international, other abroad banks, they have already started slowly kind of thing, because there is a huge opportunity for there. So, so I'll talk about a few of the use cases which banks and financial institutions are essentially exploring at this point of time with quantum and machine learning, basically. So essentially the whole the banking industry, if you look at the whole banking and finance industry, is going through a revolutionary transformation. Okay, and this transformation has started, I think 10 years back. Okay, with making all their physical services into digital services, and then putting cognitive automation on top of that, using artificial intelligence, machine learning, deep learning, and all other stuffs. And now quantum has added extra a leg or extra mileage to this transformation journey. And if you look at like now the digitization, normal digitization or normal automation with RPA, robotic process automation and all, these has become hygiene. And today, if you look at it, is more like cognitive automation. So we are using extensively artificial intelligence and machine learning kind of algorithms into different systems to make the systems more cognitively adaptable and give a seamless experience to the customer. So that is the purpose. And this is not only influencing the applications, this is influencing our products, this is influencing our processes, and this is influencing even the strategies. Okay, so it's the overall impact is versatile throughout the enterprise and throughout the organization. And QML basically, so I'll not just call it quantum, but I'll call it quantum machine learning, is one of the major area which I think in coming 2-3 years, even the Indian banks will be focusing a lot. Okay, so already in other banks like Barclays, in JP Morgan, in in Stanchart, and all other banks, Bank of America, they have already started a little bit. But in Indian banks also, the big Indian banks like ICICI, kind of Yes Bank also, I think in the coming few years, they will automatically, they will definitely start this journey. So why quantum in banking? Okay, so this is essentially because any banking industry is dealing with a humongous amount of multi-dimensional complex data. Okay, so think about, you can think of the structured data as well as the unstructured data and semi-structured data, of course. So number one is it is a data intensive business. Okay, so when it is a data intensive business, so definitely QML, quantum ML can give some kind of a real-time analysis of that data, okay, because of the humongous speed that quantum is going to provide. This definitely not all data. I'm coming to the use cases. And second thing is definitely, the recommendations, correct? So nowadays, if you look at all customers are looking at very, very personalized and very, very customized kind of a recommendation for them, right? So they don't require any kind of generic recommendation. And that is why the machine learning and QML is going to play a major role. Because today, if you look at, still we are not, whatever recommendations, whatever analytics we are running in our data, probably in our distributed data system or in our data lakes, in our customer 360-degree data lakes, it is not real time. It is still a postmortem, right? But we are expecting that it is how we can make it real time. And only solution is quantum. Definitely, if you can leverage quantum, then definitely we are going to be able to probably start giving all kind of recommendations, all kind of analytics, all kind of these things real time or at least near real time. So that is the one area. And now, as we all know, okay, so behind the scene, okay, if you look at the core of banking or finance, there are lots of complex mathematical problems. Okay, so you take any area of banking, whether it is like the trading, whether it is wealth management, whether it is normal banking, okay, or the core banking or this thing. So everywhere there are many complex mathematical problems behind the scene. Although it may look like finance, okay, fine, these are normal these things, but there are a lot of these things. Second thing is there are many areas wherein you can do optimization, and as we know, quantum is for optimization. May it be any kind of domain, whether it is banking and finance, whether it is other domain, logistic, whether it is any other this thing. Quantum is very good for any kind of optimization, and this is a field, okay, which requires lot more optimization in many areas. So that's where the importance of quantum is coming here. Okay, and also there are some amount of uncertainties. Okay, so uncertainties in the sense when you don't know the parameters or you don't know the impact of different parameters, okay, into your financial ecosystem, at that point of time it becomes uncertainty. Okay, so probably with the introduction of quantum computing, I think that those uncertainties, which we call right now as uncertainties, those will not be an uncertainty going forward. Okay? Those will be known facts because of this particular parameter. Because now there are thousands of parameters, okay, and correlating those parameters at a time and coming out of some kind of a decision-making system, it's very difficult. And that's where the uncertainty plays a major role in the financial industry. But if quantum comes full-fledged into financial systems, I believe, okay, again, it is my personal feeling that many of the uncertainties which we are talking today will not at all be an uncertainty in coming years. Okay, so we can definitely we can tell because of these parameters, these things can happen. It is not an uncertainty. So that's why there is a major focus on quantum ML, quantum machine learning in banking and finance industries, and it has already started. Banks has started already working. In India, it is very less, but outside it is quite people are doing it. Now, these are the three key areas basically where quantum can play a major role in banking and finance. Okay, so number one is basically prediction. Definitely for any kind of prediction that we are giving, so that quantum can do a lot of things. So these are mostly customer facing kind of things, or it is on customer demand. All kind of predictions can be done using quantum ML. Second thing, I talked about optimization. There are many schools. Okay, so we do a lot of Monte Carlo and all those things, and they are all kind of the trajectories and all analysis. So they are definitely quantum can play a major role. And the third is the risk profiling. Okay, so there are many risks in the entire banking ecosystem, right? So risks is one area, risks and mitigation, definitely. Identifying the risks and then finding the mitigation for those risks is one area wherein all financial institutions are working very heavily. It is a need of the day. It is not need of the day. In fact, it is without that it will not be able to survive. Okay, so as simple as that. So that area can be really revolutionized by quantum. Okay, so these are the three main areas where quantum is going to play a major role: the prediction, the optimization, and the risk profiling. And for each, under each this, there are many use cases. Okay, so probably today we know very little use cases, because see, again, quantum is not today it is not democratized, right? It has not been democratized in that way. So it is not easily available. The services are all also the cost factor and all those things are there. But once it is available to the common mass, to the developers, to this thing, then they can do things in a hassle-free way. Then I think there will be more and more use cases that will be coming. But these are three areas which now identified even the global experts and where people are working on that. So now the entire, the quantum, this thing of the entire banking and finance can be segregated into or classified into three categories. Okay, so right now if you look at, okay, but I'm talking about just the current scenario. Okay, so the future there could be many things, kind of thing. So some work is going on the capital market side. Okay, definitely that is an area which requires this kind of system. Second is credit risk side, and the third is the fraud detection side. So fraud detection side, already AI and machine learning is playing a major role. So machine learning is playing a major role. So everybody knows for any kind of fraud detection system, whether normal transactional frauds or if it is kind of anti-money laundering kind of a thing. So it is already AI and machine learning is playing another role, and it is already been adopted in most of the proven solutions today, because you require an adaptive system for this, right? I mean, because any kind of fraudulent activity, if you look at this, fraudsters are maturing, right? They are also becoming more and more intelligent. In fact, they are also scientists. Okay, so they are also doing a lot of research work, and because of that, you require an adaptive system. So your rule-based systems, which we have been using, so banks has been using this kind of fraud detection system for ages. It is not a new thing. Okay. But the problem with those systems were like those are only those are basically templatized, right? If it falls under, if the fraudulent activity falls under that particular template, then only it can detect. But if somebody comes up with a newer technique, okay, then this rule-based system, although there are many, I mean, couple of thousand lines of codes has been written for each rule-based system, but it is not been able to detect those kind of fraudulent activities. So that's where a machine learning model, which is adaptive, basically, or even a deep learning model today, okay? So using neural network is much more efficient than that. But now how quantum is going to play a role here is essentially to run those algorithms into quantum so that we can get it in a much faster manner and much efficient manner also. So that's where it will be coming. So already it is there. So I don't think so there is any fraud detection system available today, which is basically rule-based, purely rule-based. So it could be a combination of ML and rule-based, but it is not rule-based because you require an adaptive system. So that is one area. So there could be the frauds are, I mean, and then this fraud, the entire fraud landscape, if you look at, it is versatile, okay? And every day it is growing, okay? So initially it used to be only credit card frauds or transactional frauds. So now there are many, like anti-money laundering is there, wherein like the illegitimate money is coming into your legitimate system and it is going to cross-border for terrorist funding or kind of things. So how to detect like whether where from this money is coming and then distributing and going cross-border. Okay, so cross-border transaction, and then it is being again withdrawn by different parties for different kind of illegal activities. So detect those kind of systems. Actually, you require a network diagram, and wherein you can see how the money is flowing from one direction to another direction, kind of thing. And there are many advanced systems now coming up. There similarly tax fraud is there. The instant transaction frauds are there. Many frauds are there, and everywhere machine learning and quantum is going to be a killer combination, basically. Okay, so the fraudsters should be very now they should be aware of that this is coming. In the credit risks, so there are many credit risk models which are available right now. If you look at, so people are also doing behavioral analytics. Okay, before giving you any kind of credit. So it is not only employing a normal vanilla statistical machine learning models, but also different kind of very advanced machine learning models to understand the behavior of the person, how reliable he is, or what do you call, how reliable he is that he will be able to repay the loan. or how reliable he is, so that we can give him some kind of a financial aid, and if yes, how much. Okay, so that can be done very, very intelligently. Okay, and the percentage of accuracy of this kind of systems are more than 85-86%. Okay, so it's very, very intelligent. So there also quantum is going to be. Portfolio supervision is another very, very known use case. Simply buying propensity of the customer. Okay, so what is the buying propensity of the customer? That you can analyze and you can see, and there. So here, none of this is a pure quantum case, right? Because I mean, in banking and finance, it is a quantum case. There is nothing like that. It is quantum ML kind of thing. Okay, so I don't know in other kind of things. I think in most of the industries it will be like that only. Okay? So quantum alone cannot help somewhere. So it will be the combination of something. Capital allocation optimization. This is a big optimization problem still today. Okay, so how actually you can optimize the capital allocation?
No, 867.
Could you please put your mic on mute? I think some. Okay. Yeah. Thank you. Thank you so much. And now coming to the capital market. In capital market, portfolio optimization, very, very important thing. Then optimal trajectory is another area wherein there is a huge focus and where we require a system like quantum. Any kind of trend or anomaly detection, okay, that is also an use case. So is it again a machine learning kind of a use case? Market crash prediction. Okay? So this is again where quantum will play a major role because this requires speed. Okay, kind of thing. So coming to these are the potential areas where like quantum is already either implemented or people are already doing kind of things. So many of the, I think many of the algorithms are also available now, and people can actually start exploring, testing, and all those things. I think many of the providers, including your IBM, then recently, like Microsoft Azure has also launched their quantum services. Then DUAB is there, so DUAB also have, and DUAB is their focus is into mainly into the financial sector, and they are doing a lot of work on the financial sector. So there also you can do. So these are some of the areas. So you can actually look at the investment gains. Okay, you can look at any new investment opportunities or possibilities that you can see. You can see how where you can actually reduce capitals and all those things. Compliance related things, again, there also you can apply any kind of compliance, and risk management, of course. Risk management is one of the odd areas. Now coming to where to start. So if a financial institution, probably they may ask that question. Okay, fine. So these are new things, very, very exciting things, how we can start our journey. So same question has been asked at the time of when artificial intelligence was very, very hot. Okay, so at that point of time, I was working in a different industry, and most of the times I used to meet the innovation heads of banks and all those things. So they were asking the similar question, Uppal, how we can start. Okay, so still for many banks who has not started their journey, still their question is like that, how we can start our AI journey or kind of things. So same question for financial institutions are where they can start their quantum journey. Okay, and I think already Microsoft has started doing that industry collaboration kind of thing, and they have started building COEs in India also. In some of the banks, they have just started. So first of all, explore some quantum use cases. Okay, you can take the advice of some quantum expert or any academia like you. Okay, so because you people are doing actually the theoretical part and the conceptual and the actual mathematical part of it, they can discuss with you also, because your researchers and all those things, and try to find out some small use cases which can be implemented into the financial institutions. Probably you can, in the second step, you can build a small COE. Okay, because once you build a COE with 1 or 2 or 3 resources, you can start exploring some of, probably you can appoint 1 or 2 quantum experts or who are doing some research kind of thing. And then the financial institutions, they can start building that team and start experimenting, doing some proof of concepts or pilots. Okay, and first, my recommendation to the financial institutions is first try to see or explore some of the existing algorithms rather than like out of the box going into, I mean, start writing your own or building your own circuit and all those things. Don't go for that. First, look at some of the existing capabilities already available, okay, and try to see how it works and all those things. Because as it is an evolving field, right? So still it is maturing. So probably if you invest a lot, so investment also you need to see a lot of time and a lot of resources and a lot of these things. So probably it may not work at the desired level. So definitely it is going to work, but I mean, again, it may not comply with the success criteria of the pilot or the POC or the project. So try small things first, and then start implementing. And also the partnering with different vendors, providers, and academia is very, very important, because they are also doing work into different levels. And if you partner with them, if you can do knowledge sharing with them, then definitely it is going to be a win-win situation for both the parties. Okay, so they probably, financial institution can partner with academia like you, who are already working in some of the things. Similarly, they can partner with the providers like DWeb, Microsoft, IBM. Okay, so there also they can do partnerships. So these two levels of partnerships are very, very important because that will definitely give some kind of a mileage to their projects and all those things. Because this is a new field, and definitely we need to collaborate, and we can do it in that way. So this is something which I feel any financial institution or any institution for that matter, they can any industry, they can start in this kind of a way. So we have started the AI journey also in the similar way. Okay, nothing different. Now coming to some of the challenges at this moment. So right now there are some challenges. So that we should be cognizant about the fact. So I think from my studies or from my this thing, I think it will take another couple of years to get things a little bit in a better shape. So that is one thing. The cost is another thing. Only big financial institutions can actually, for real use cases, they can afford at this point of time. Okay, for small financial institutions, I think I'm not sure. I mean, until and unless it is very, very compelling, whether their budget and all those things, innovation budget and all those things will support for those kind of things or not. But for big and medium financial organizations, definitely they can afford and they can do. Third thing is the widespread availability of these systems. So I think this will, in coming 2-3 years, I'm sure that this problem will be solved. So, but right now these are some of the challenges at this point of time, which I feel. So with that, I want to conclude here. So if there are any questions, any comments, any suggestions. So because this is a new field, it is not like somebody is expert or somebody is a kind of thing. So we all are learning, and definitely we are actually sharing knowledge. It is not like taking sessions or something like that. No. Yeah.
Thank you very much, sir, for a wonderful talk. And so we are looking for any questions. So meanwhile, I have just one query that, yeah, you mentioned that outside India, like in US, banking systems have well adapted these things. So do you think that in India, means how many years approx it will take to adopt by Indian banking system to these wonderful AI technologies for the customers?
They have started actually. That's what I mean. I'll not be able to take the name of the bank, but Microsoft, along with that bank, okay, because I know Microsoft people pretty well. I mean, the people who are working in the quantum area and AI area. So they have already started building a COE, okay, and they will be exploring some of the use cases in one of the leading bank in India. Okay, so definitely that is a big bank, and they have got that fund and all those things. So and in India, right? Once one bank starts adopting, you will see within a couple of years, everybody will start. So the first mover is very, very important. Okay? Who starts the first? So I think it is not a couple of years. I think in coming 1 or 2 years only, you will see at least 1 or 2 banks will have some kind of applications ready, which will be using some amount of quantum computing, and that is going to be a big success, because starting is very, very important, and later on the adoption goes very, very fast. So that's what I this thing, because I know this information that they have already started building that COE with 2 or 3 experts, quantum experts from Microsoft and these things, and they will be started building some of the applications very, very soon.
Yeah, could you please take over the things?
Okay, thank you very much, sir, Mr. Utpal Chakraborty, for sharing your valuable knowledge and your time that you spared with us. And we really get it very useful for us to at least get the encouragement to start with the new research on this, or the new knowledge on this topic of quantum computation in engineering and medical sciences. Thank you very much for being with us. And now we would like to take the session of Professor Dr. Debashish De. That would be a joint session along with Mr. Sudhindu Kumar Mandal, who is the Registrar of Regent Education Foundation. So we want to take that joint session, wherein apart from theory, most of the thing would be as promised by them, that most of the thing would be basically on practical. So we are very encouraged to get all these knowledges. So I would request again to Dr. Dhananjay sir to please read out the brief profile of the speakers of the next session, joint session of Professor Dr. Debashish De along with Mr. Sudhindu Kumar Mandal. Sir.
Thank you, sir. So again, it's my pleasure to introduce our 2 next speakers for the joint technical session, Professor Dr. Debashish De and Mr. Sudhindu Mandal. So Dr. Debashish De is professor in Department of Computer Science and Engineering and Director of School of Computational Science at Maulana Abul Kalam Azad University of Technology, West Bengal. It was formerly known as West Bengal University of Technology. He is also an adjunct research fellow at the University of Western Australia. He has awarded the prestigious Boaz Cast Fellowship by the Department of Science and Technology, Government of India, to work at the Heriot-Watt University, Scotland, UK. He received the Endeavour Fellowship Award in 2008 by TEST Australia to work at the University of Western Australia. He received the Young Scientist Award in 2005 and 2011. In 2016, he received J.C. Bose Research Award by IETE New Delhi. He is a recipient of Shiksha Ratna Award from the Government of West Bengal in 2019. His research interest includes mobile age computing and Internet of Things. He published more than 300 peer-reviewed high-quality papers and 100 conference papers and has filed 9 patents. So he has published 8 research monographs with world-class publishers such as CRC, Springer, Nova, Elsevier, and 5 textbooks in Pearson. His I-10 index is 121. We can assume. So, and H index is 30 and citations more than 4,500, which shows his extraordinary contribution in scientific domain. So again, I will introduce our second speaker for the joint session, which is Mr. Sudhindu Mandal. So Mr. Sudhindu Mandal is a quantum computing researcher whose main research fields are quantum algorithm, quantum circuit, and multi-valued quantum systems. He has more than 13 years of experience in the field of education. He worked in an important project funded by DRDO. He worked as an assistant professor in University of Calcutta. Presently is working as a registrar in Reagent Education and Research Foundation. He has 7 journals and over 10 conference papers. Recently, his paper One-Dimensional Lazy Walk in Ternary System is accepted in IEEE transaction. He is also the badge holder of IBM Quantum Challenge and IBM Quantum Challenge India. He is proficient with quantum computing language such as Qiskit and Pennylen. So with these all, I would request Professor Devashish Dey sir and Sudhendu Vikas Mandal sir to please share his thoughts and knowledge with us. So please, sir.
Very good morning to everyone. Thanks to Dr. Mithun Chakraborty and Dr. Dhananjay Kumar Pandey and the Vice Chancellor, Registrar, everyone, those who are organizing this quantum event today. And I must say it is basically an awareness event for quantum computing, because if you want to take a class or other lecture on quantum computing, it will take maybe 100 hours. So, but with the next 1 hour, myself and Sudhendu want to give some glimpse of how we are actually implementing this quantum computing in our practical life. The quantum computing is, I'm using this word quantum computing or rather quantum devices for last 20 years, since 2001. And that time the quantum computing was a dream, not a reality. But as you have seen, Professor Siddhartha Bhattacharya has already mentioned in his lecture, and he has shown how to log into the IBM quantum computer and how to access the computers. So basically, in a single line summary, that quantum computer, is basically reality, and we are all accessing this quantum computer. Today, Sudhendu will show you the practical part by accessing the quantum computer and to develop the logic gates on it. There is some question that whether if the quantum computer comes, is it like our own laptop or computer? Answer is no. Our conventional laptops or our computers will exist, but we will access the quantum computer in a form of cloud. Okay, just like the login, Professor Bhattacharya has shown that we have to access the quantum computer using the login, and that computer is basically confined in a very low temperature, cryogenic temperature, minus 273 degrees centigrade, because the quantum device cannot work in the room temperature. Okay, that research is the problem. That is the reason we cannot have quantum computers at home. We have some wrong conception. So we'll be accessing these quantum computers in various parts of the world, and you'll be happy to know that I've worked in some of the projects in UK as well as in Australia, and I was fortunate to have hold the quantum computer in my own hand, and we worked for several months on it. So I'll just try to give you some glimpse of it. So some of the pictures are not allowed to permit and show in the online mode, so I will not be able to share it. But I just want to start with the point that since childhood we heard about that ABCD, right? A for apple, B for ball, and that is my topic is Q for quantum. And this is not the dream; this is the reality. So just like the A for apple, B for ball, quantum is part of our life, and for next 1 decade or several decades, we'll be basically running our systems using these quantum computers. Okay. Now, if you're talking about quantum computing, it starts with the nano devices, nanomaterials and nano devices. So if you see the devices in this nanostructure mode, you see, basically we are having quantum well, quantum wire, and quantum dot structure. Normal materials, it starts with materials, semiconducting materials. As you know, it is bulk material, normal material. It can be silicon, it can be gallium arsenide. If we quantize some of the site, means what do you mean by quantization? You have to reduce the dimension. So if it is a square cube, And if you reduce the dimension, say this x-axis, this is it forms a well. That means your energy is confined. All the particles of this box, say there are say 1,000 bubbles in this box, that will be confined within this small area. So it is just like a well. And if you confine x and y axis both, it forms a wire. You know, just like a single, just like a pen. You know, it's like a forms like a wire. That means electrons can move in a single dimension, one dimension. Okay. And if you quantize all the direction, it forms a dot, just a tip. So you understand, when we are combining all these materials, we are quantizing means we are reducing the dimension. Now, what is the dimension? It should be below the 100 nanometer. The dimension must be below the 100 nanometer. Okay. So by this way, we are quantizing, and in quantum dot is more powerful because all the 1,000 balls or the dots are basically combined within a very small space. So it is much more powerful. So if you see the energy is continuous. When you are talking about quantization, energy becomes discrete. It will become more discrete. So if you see the quantum dots, energy becomes much more discrete. Using the IBM or Google Cloud, actually, the scientists has developed the quantum computer using these three basic nanostructures: quantum well, wire, and dots. Okay. So we have done extensive study to develop these models or these dot models and these nanostructures using these quantum computers. Okay. So if you see bulk, there is no confinement. It is 0 dimension confinement. For quantum well, it is 1 dimensional confinement. For quantum wire, 2D is confined. Quantum dot, 3 dimensional is quantized. So it is no free path is there. Quantum dot means full quantized. Okay, and using this quantum dot, actually, that is a basic starting point of quantum computer. So that dot is much more powerful. So all the concentration of the electrons are within this dot. That is the reason it becomes much more powerful. So quantum dots are very, very powerful. And you see, for last since 1993, Professor C.S. Lent has shown a model. It's called quantum cellular automata. So they have considered 4 dots, and this is a blank. This is a 2 dot filled up. If you place the 2 dots, means 2 electrons like this diagonally, we call it logic 1. See, 2 electrons cannot be in the side-by-side state. They will repulse. There will be a repulsion. So after the repulsion, this electron will jump to this place. Now, if we change the position from this dot position to this dot, so this dot will be coming to this. So by this way, we are forming logic 0 and logic 1. Everyone know that our computer understands the logic 0 and 1. So we developed this 0 and 1 model using this quantum cellular automata. So by this way, we have developed the majority voter, A, B, C. These are the 3 logic blocks. You can see this is 1, this is logic 1, this is logic 1. Obviously, this 3 will basically influence the middle cell. If you see the 3 input, A, B, C, when you're talking about AB, it becomes AB, it is BC and CA. So if you know the formation is output, if you consider this is Y becomes AB plus BC plus CA. That means based on the level of polarization of the electrons, the output is controlled. By this way, we can develop various, this is called majority voter. We can develop various logic and logic. So if you're interested, you can go to this quantization. We have published some books on, for last 20 years, we have published these books. One is on quantization for photo emission materials. Another one is for Einstein relation, and third one is for quantum dot cellular automata. So if you are interested, you can go through this, right? Next, another very interesting things are coming up, that our human body, we are talking about our human body is working with various unconventional logic. Say, for example, in our hand, we move our hand. So, for example, if there is a mosquito sits in my hand, next hand will bit the mosquito, right? There is some logic. What is the logic? That if the mosquito is there, my other hand will come and it will kill that mosquito. That is a physical things are happening in our body, and that is also quantum inspired. And actually, that we have explored that there's a molecule, basically it's called proteins are there in our body. It's called actin. It's called actin protein, and that is also one kind of quantum molecule, and that works in the same logic of quantum dot cellular automata. And if we follow that logic, then our hand movement, leg movement, everything is controlled. So there are lots of quantum phenomena is basically actually happening in this logic modules. And we followed the basic laws of cellular automata to form these logic systems, right? So if you see, this is the actin is playing a major role. This actin-based QCA started by Professor C.S. Lane. He is from UK and Bristol University. He developed a laboratory for actin quantum dot cellular automata, and he developed these modules. Basically, through these modules, we can understand the how our hands moves, how our leg moves, how our body parts moves, and that is based on our quantum dot cellular automata, rather quantum operations, right? So see this inputs and output control is basically controlled by this logic, and this logic block is basically each and every block is nothing but an actin molecule. That human body is made up with molecules, so there are various gates. Our body, there are various molecules are acting as a gate and or not gate. Even there is also actin multiplexer, actin demultiplexer. So you understand whatever the logic we have studied in our digital electronics paper, and that digital electronics logic in terms of quantum is also available within our body. So we are trying to explore this this philosophy, and that forms this this logic operations. So QCA is actually happening in semiconductor, as I already mentioned, well-wired dots. It is also happening in molecules. Even it happens in metal also. If you take a gold, what is the color of gold, Mithun sir?
Yellowish. So it's
Yellowish, right?
Yes.
If you quantize that gold, it becomes red. Okay. So if you want to sell this red gold in the market, the people will come and beat you, right? Red gold. Okay. But actually it is happening. So in terms of this nanotechnology, we are doing this magic, and we are converting, actually we are using this semiconductor-based quantum dot cellular automata or quantum computing, molecule-based quantum computing, metal-based quantum computing, and magnet-based quantum computing. So these are the basic 4 areas. So Google, IBM, both are working in this this semiconductor-based system, but some of the scientists, they are working in this molecule-based systems. And you'll be happy to know that our research group is world's #1 in terms of quantum cellular automata systems. If you go to Scopus, you'll see our university, rather our research group is coming in the top of this quantum cellular automata operations. There are various fields there, various logic. So actually using this quantum computing, you have to build up the logic first. If you can develop the and or not logic, what Shudhindu will show you today, after some times, if you can build up the logic, you can also develop the multiplexer, you can develop the ALU, arithmetic logic unit, everything. So we are exploring this all the possibilities, and we are working on this actin-based logic also, right? I just want to give you some basic idea. The interaction of the molecules within the body that is forming the logic, right? So if you see the cells, I'm not going in detail, the cells interaction, we are forming this logic. There is some cellular automated rules. Those who are interested in automata theory, which is very important for state change. That in terms of, say, combination logic or sequential logic, we have previous state and next state, right? Previous state and next state is controlled by some logic, and that logic is basically within our body, and that is controlled by these actin cells. So I'm not going in detail, just I want to give some glimpse of it. So these molecules, that interaction form these kinds of quantum phenomena. Okay. So there are some rules. say 427 rules are there. There are hundreds of rules are there in cellular automata. Actually, here we are following these rules and we are exploring these operations in the molecular domains. And we are mapping our cellular automata rules to these actin-based molecules. So this is basically body logic, human logic, how this human molecules works, and that works in the quantum phenomenon. So 0, 1 and superposition theory, everything is controlled by this. So I'm not going in this. I just want to give you the basic idea. So we have also developed this XOR gate and AND gate. We have developed this multiplexer. We have published these papers in microsystem technologies, and in 2017, right? How we can see that we have developed the XOR gate using actin quantum automata, means which is within part of our crypto analysis, right? So we have also developed the substructure molecules, binary substructure using QCA, which is published in IET journal. IET is a very popular journal. If you are interested, you can go through it. How this actin quantum cellular things works. Also, we have developed this ALU, arithmetic logic unit, right? ALU is a basic part of computing for any kinds of which follows a von Neumann architecture. So we Biplop and his group, our group has developed this all the molecules based unconventional logic unit. Also, we have developed the very interesting. First time we have developed the nano communication. Within our body, everything is there is a transmitter receiver, and we call this communication called nano communication, just like our normal transmitter receiver. And this is also happening through these quantum operations. So everything is quantum based and quantum molecule based, right? So I have shown you semiconductor based operations, and this is all molecule based operation. And we are continuously working in this domain. So today we will show you the qubit. In case of classical, we have 0 and 1. And in case of qubit, we have a third state resultant of the superposition. What is the beauty of this third state? We can have large amount of data. We can do a lot of computation because of this third state. Because of this third state, we can compute in a very short span of time. So in their previous two lectures, speakers are talking about banking sector and various other sectors. And also Siddhartha sir mentioned about in COVID time, the drug design, everything is happening due to this third bit, because that increases the computing power because of the superposition. So qubit is very, very popular. So we will develop this qubit practically on the quantum computers. And this is the IBM Q picture. And I took this picture from net. And but I also have one selfie kind of thing. In 2003 and 2016, we worked in IBM Cloud, which is in Melbourne University. And Sudhandu will give you some basic discussion on it. And earlier it was 2-bit and 4-bit. Now it is 64-bit. Even people are talking about 400-bit. Even Google, Google quantum computer, very popular Indian scientist is here in front of you. They have developed something new, which will help you in quantum search, right? I think many students are present in this as an audience. The quantum searching will become very faster. So when you're talking about Google search in the year of 2005, when I was student in 2002, that time searching one page takes several minutes. Now within a fraction of a second on your mobile, you are searching Google, right? Now using these quantum computers, Google will make this search much more faster. So at the speed of quantum speed. That is the beauty of quantum computing. That is the power of quantum computing. So there is always a fight between quantum supremacy between Google and IBM. And some people are telling Google is much more ahead to IBM, and there is even Google is not disclosing any data. They are practically applying their data in their quantum search, Google search, right? Whatever you are searching on Google, that has been reflected by this Google search. And in terms of IBM, IBM is doing a great job for us researcher because IBM is giving free access. Mind it, Google is not giving any free access to all the researchers till date. And IBM is giving free training and free access to these quantum computers. I think this is time for Shudindu to give you a details discussion how this IBM Q actually helping us to develop the modules like quantum machine learning, quantum neural network, and all these details events, right? Thank you. Shudhu, over to Shudindu.
Thank you, sir.
Yes.
First of all, very good afternoon, all of you. I would like to thank Dr. Mithun Chakraborty, Dr. Dhananjay Kumar Pandey, and our Honorable Vice Chancellor, Professor Raman Kumar Jha. And I would like to special thanks to Professor Devashish De for suggesting my name for this seminar. And now in this session, I will discuss with some simulation technique of quantum circuits. Basically, you can create your own quantum circuit and simulate it in your local machine as well as in the IBM computer machine. If you allow, before going to this simulation environment, I want to discuss a little about the linear algebra because it will give us a more visualization regarding quantum circuits and all the things. I think our previous speaker, Siddhartha sir, already discussed, touch everything, I think, and it will help me to, it actually reduce my job. Okay. So before going to the simulation environment, I want to show some little bit about linear algebra. Okay. If you allowed. My whiteboard is visible, I think.
Yeah, visible.
Yeah. First of all, already almost all of the speakers tell what is qubit. From the very beginning of this seminar, uh, uh, Professor Raman Kumar Jha also tell what is qubit, and also Siddhartha sir and Devashish sir also told that what is qubit. And I'm writing this one is our qubit is like psi alpha 0 plus beta 1. And this bit is a probabilistic bit, and there is a lot of uncertainty, and it is already told by Professor De. And presently we are using our classical machine. Classical machine actually a deterministic machine. So this qubit gives a lot power. And there is another things, these alpha and beta are both are complex number, and qubit exist in a Hilbert space. And Hilbert space, what is this? Hilbert space is a complex vector space, and I will not discuss more about the Hilbert space, but there is another condition exists. This is mod of alpha square and mod of beta square should be 1. This is already told by the our Vice Chancellor sir and also by Professor Siddhartha sir. And what is that? This one is the actually norm of the qubit. And when we'll do any operation over this qubit, we have to preserve this norm. That is, suppose there is some quantum operator A. If we applied with this qubit psi, we'll get another qubit. This one should be a psi dash. And within this psi dash, we should have to preserve these properties. Basically, we have to preserve these norms of the qubit. So how can we preserve these norms? Already, Professor they and Professor Siddhartha sir also told that each and every quantum operator is unitary. This is the, for preserving this norm, unitary actually acts major role. Unitary, what is the unitary means? U and U dagger should be a identity or we can say uh, that means within this matrix, each and every element, if we sum up with the row and columns, it will act as a stochastic matrix. Okay, and see by an example, what are the different operator in quantum computing? There is a 1 qubit operator, and what are the different 1 qubit operator? Already says there is Pauli X, Pauli Y, and Pauli Z operation exist, and along with there is exist a Hadamard. And already Siddhartha said show the matrix representation of Pauli X is 0, 1, and 1, 0. See that this one is a unitary operator. Why? It's sum of this column is 1, and sum of the each and every row is also 1. And by this property, if we apply with any qubit, then we can actually preserve the norms of this uh, 1. This we can preserve the norms of the qubit. And physically you can visualize qubit. Each and every point exists within the unit sphere, or specifically we can say within the globe. If you find any points on the surface of the globe, all are the valid qubit, and this globe should be a unit sphere. Now I am discussing some basic things of how can we simulate. Basically, in case of quantum simulator, there exist two basic component. One is quantum register, another one is classical register, and the quantum gates. QG, I defined it as quantum gates. This is a basic component of any quantum circuit. This is a basic component. And when we want to design any quantum circuit in our simulator, we have to initialize quantum register, and we also initialize the classical register, and we have to apply some quantum gate within this register. And for better visualization, in our classical computer, actually a spatial circuit. But in case of quantum, it's not a spatial circuit, it is a temporal circuit. Actually, there exists a register, and we are doing some operation within this register. We are not like this. In classical, there is a register, and there is some classical wire, and there is some gate and everything. And after doing this operation, we'll get output here. In case of classical computing. But in case of quantum computing, there is no existence of quantum wire. Actually, there is a SHI, and this SHI is called a register set. And within this register, we are doing some different operations by using the quantum gate operations. And after completion of quantum gate operation, we will get the final register. And this one is the final result. After that, we will measure it and gets the classical output. Okay, this is the basic difference between classical computing and quantum computing. Now, in quantum computing, there is a two type of bases. One is 0-1 basis. Another one is, we have already seen, Hadamard basis. This one plus and minus. Actually, this basis is the eigenstate of our Z operator. That means Pauli Z operator. This one is the eigenstate of our Pauli Z operator, and this one is our another basis. This basis is actually the eigenstate of Pauli X operator. See, we know what are the, already we have seen in the previous lecture, what is the matrix representation of X gate. This one is 0, 1 and 1, 0. Another one is what is the matrix representation of Z gate. This one is 1, 0 and 0 minus 1. This one. So if we apply X gate within the 0 basis, we will get 1 because X gate is acting as a NOT operation. How this operation is acting, I will show. And if we apply X gate to the 1, we'll get a 0. And in this basis, if we apply Z gate with 0, it will act nothing. It will remain same. If we'll provide Z operation with apply 1 gate, it will give you the -1. Actually, it rotates its phase. And so within this basis, X gate actually, Pauli X operator actually act as a NOT gate, and Z gate is actually act as a phase gate. But in case of this basis, Hadamard basis, here Hadamard basis means plus is actually a 1 by root to 0 plus 1 by root to 1, and another one is -1 is 1 by root to 0 minus 1 by root to 1. And if we apply x into z, what will happen? We'll get 1 by root to 1 plus 1 by root to 0. Basically, x is a NOT gate. It converts 0 to 1 and 1 to 0. So it is same like a plus operation. But if we apply x into the minus basis, it will give you the 1 by root to 1 and minus 1 by root to 0. So what will happen? It will give you the minus basis. So in this case, Pauli X operator actually work as a phase operation in this basis. Here x is act as a NOT operation in the 0-1 basis, but in case of Hadamard basis, X operator is works as a phase gate. But if we apply Z operation with +1, we will get actually minus if you do this computation, and if we apply Z operation with minus, you will get a plus operation. So what will happen here? Z gate act as a NOT operation within this plus minus basis. This is very important in for designing the quantum algorithms. If we want to design a quantum algorithm with like Grover's algorithm or any other source algorithm, or if you want to design basically one very basic part of Grover's algorithm is phase kickback, and this property is very helpful to design a phase kickback in case of quantum designing the quantum algorithm like Grover's algorithm. Okay, I will not discuss more about the linear algebra. I will just describing the what are the different part of the simulator. Basically, I will discuss in our environment there exist so many simulators to simulate your quantum circuits. There is provided by the IBM, and the simulator is provided by the Xanadu, one of the famous quantum computing company. Another is also provided by the Google, but in this lecture I will discuss or concentrate on focus on the only on IBM Qiskit, IBM simulator. In case of IBM simulator, IBM provide two type of simulator. One is graphical simulator and another one is coding based simulator. In case of coding based simulator, they are providing a Qiskit language. Qiskit language is developed over the Python programming languages, and IBM provide another simulator. This is called a GUI based simulator, which is we have already seen by the Professor Siddhartha sir, and I will come this picture. In this session I will discuss both Qiskit and as well as GUI environment also. In this Qiskit simulator, they provide three type of simulation environment. One is chasm simulator, This one is a quantum assembly language simulator. Another one is state vector simulator. And third one is unitary simulator. All these three are simulated, but after simulating my quantum circuit, we can actually execute our quantum circuit in a real quantum hardware also. This one is a real feelings for us. Here from the far away from the quantum device, we can execute our quantum circuit in a real quantum hardware. This is also provided by the Qiskit language, and this is by a IBM Q simulator. And this is not a simulator, this is actual quantum hardware where we can execute our quantum circuit. In this GUI mode, we can also we can simulate the chasm and also the real hardware. This is the basic difference between Qiskit and GUI mode. You can also see the state vector little bit, but unitary vector simulation is not provided in the GUI mode. Okay. So let's go to this direct hands-on there. I think my Jupyter notebook is visible to all of you. Here, before writing any quantum circuit or something, we have to import some uh, package from the Qiskit. Before writing any code in Qiskit, we have to install Qiskit. You can install Qiskit from the qiskit.org, or you can go to the GitHub also. From here you will get a link, and after getting, and for installing the Qiskit, only one prerequisite is there. You need to install, before Qiskit you have to install Python 3. And after doing all in this within this limited time, I will not show the how can we install Qiskit. If you feel if you get any problem, you can ask me in later via any communication via Professor Dr. Mithun Chakraborty or any other. You can communicate with me if you feel any problem to install Qiskit. Okay. And in our machine, I have already pre-installed Qiskit, so I can import the package. One is the vital package is quantum circuit, quantum register, and classical register, and also the assemble and AR package. AR package actually provide us the main backbone of this different backend of the quantum simulator. So first we execute. So in case of, if you want to define or if you want to simulate your own quantum circuit, first of all you have to define the quantum register. So first define as quantum register is QR. Suppose I want to design a 2-qubit just 2-qubit quantum circuit. Okay, here QR is equal to, we have to write quantum register of 2 qubit. So I have create a quantum register. Now we have to define a classical register also, because we know quantum world is a probabilistic and uncertain world. To get the result, we need a classical register also. That's why we have to create a classical register, and this one is CL. So this one is our classical register. Now for creating the quantum circuit, we need another one is, this one is quantum circuit, and this component of this quantum circuit is quantum register as well as classical register. This one, if we want to print this circuit, you just write qsig dot draw.
Shubhendu sir,
Yeah. Hello.
maybe interrupt sir, your screen perhaps is not visible.
Which one?
Sir, your screen perhaps is not visible.
My Jupyter notebook is not visible.
Jupyter notebook is visible, but whatever you are doing,
Oh,
perhaps these are not.
I think I have to magnify. I think just now, if you want to see that Sorry. Okay. See, this one is our quantum present quantum circuit, and it's give nothing nothing is visible. Basically, I didn't put any kind of quantum gates. Now we have to put some quantum gate here. Now I'm putting some quantum gate. Suppose our quantum circuit is like that. I want to put here Hadamard gate, and Hadamard gate is mentioned by H. I want to put Hadamard gate in the first qubit. So there should be a H0. Now I want to put another gate. This one is QC dot control NOT gate. Say, and its control part is from 0 to 1. So now if we want to draw this QC, yeah, see, this one is our quantum circuit. This is our first quantum circuit, and now we have to simulate this quantum circuit in our different simulator. First, I will simulate it in a state vector simulator. Then I will show it to simulate within a unitary simulator. Then I will show you the chasm simulator also.
I think it's not visible. Shouldn't it is some problems again?
Still,
The screen means the bar, localhost. I don't know.
Circuit is not visible what you have created.
now
No, it's not visible.
this is also not visible, sir.
Yeah. Can you just recast means reshare?
Or
Only
you
the
can share your screen also. Entire desktop screen you can share.
yeah.
Okay. Just now.
Now it's visible.
Now
Yes.
it's perfect.
Thank you.
It's
Now
visible.
it's visible. Yes.
Sure. And this one is our first circuit we have designed. Now we have to define which type of backend we will use. So I'm defining the backend. Same is equal to in for defining the backend we need a ER package.
But I think you can ask whether everyone is understanding or not, because it is a new, just a new, very new thing. Can you just repeat because no one can see this.
Actually, I am also telling the same because we could not see where from you have started creating the circuit.
Yes.
Kindly reiterate.
Okay. First of all, just I'm showing another things. Is there any whiteboard? Okay, let's. First of all, I want to create some quantum circuit in a Qiskit environment. Basically, in previously I told there is a two type of simulator exist in provided by the IBM. One is GUI based and another was language based. And first I will show you the I'm showing you the Qiskit language based simulator. Here, before I've told before writing your any quantum circuit, you have to install the Qiskit language first. And for installing the Qiskit language, you need to install as a prerequisite. We have required a Python 3. That's enough. First of all, in this machine, I have already installed Qiskit. That's why I am importing this import quantum circuit, quantum register. Basically, previously I told for defining the any quantum circuit, we need three basic components. One is quantum register, another one is classical register, and another thing is quantum gates also. And there is so many 1 qubit, 2 qubit, and 2 gate is provided by the Qiskit language. That's why I just import this quantum register, classical register, and also we have required a backend for simulating like unitary backend or uh, state vector backend. That's why I require to import the AER package. I'm showing where is AER package, and here is AER package also. And to plot our quantum circuit or quantum something, we need this visualization plot. Okay, So in the first step, before going to design your quantum circuit, you have to define a quantum register. Here we are going to define 2-qubit quantum circuit. So we need a 2-qubit quantum register. That's why I am taking keyword is object of, actually the object of quantum register, and we are calling the class quantum register and passing the value 2 with this the constructor of quantum register, and it will creates an object of quantum register of 2 qubit. After that we define a classical register, and for defining this classical register object we need a class classical register, and within this constructor we have to pass the how many bits to define. And here we are going to design a 2-qubit quantum circuit. That's why I pass here 2. And after that, we have to design a quantum circuit, and quantum circuit has 2 parameter. One is quantum register, another one is classical register. And that's why I put here QR and CR as a parameter of this quantum circuit class. And I put QR and CR. After that, quantum circuit will create by our cascade, and I'm draw the basic quantum circuit here. One is quantum register Q00, and Q01 is the second quantum register, and C00 is our classical register, and C01 is our another classical register. As we have designed 2-qubit quantum register and 2-qubit classical register. This is presently exist in our quantum circuit. Now we want to assign some quantum gate within this our quantum circuit. So I want to assign a Hadamard gate in the first qubit line or in the first qubit register. That's why I called quantum circuit object dot Hadamard gate, and I mentioned the position of the Hadamard gate, where I want to put this Hadamard gate. That's why I pass 0. That means it will stay within this quantum register 0. And after that, I want to put another quantum gate, that this one is control NOT gate. And in control NOT gate is a 2-qubit gate. It has 2 bit. One is a control bit, another one is a target bit. And I want to put it as a control bit to 0 qubit register and target to the 1 qubit register. That's why I here put qc.cx. Cx means control NOT operation, and here control NOT operation actually takes 2 parameter. One is we have to mention the which one is our control bit and which one is our target bit, and I mention as 0 as control bit and 1 is as target bit. After doing that, I draw my quantum circuit as qc.draw. Just if I want to change the control bit and target bit like that, if I put control bit as 1 and target bit as 0, then what will happen? See, this one is our third, I mentioned here, third quantum circuit, and this one is here our control bit, but I have to run from the beginning, then it will be more better. Because now see, in the previous example I use control bit as a 0 and target bit as a 1. That's why it was from first qubit 0 was a control and target was a qubit 1. But here I just reverse the control and target. Here I use control bit as 1 and target bit as 0. So here you see control position is shifted to 1 and target is shifted to the 0. But I want to see different circuit. That's why I just go to the previous one. I want to change it 0 and say again I shifted it to the in my previous circuit. Now I want to simulate it into a state vector. That's why I need a backend, and this backend is by Backend is provided by the AR package, and within this AR package there is a method get backend, and here I mention the backend is as a now. uh, Now we have to run this our circuit to any other here. So we have to first uh, assemble our quantum circuit by using the assemble package, and this will provide the ready circuit to our quantum simulator. That's why we are designing Q object by using a assemble of our QC. Now this is ready for running in our simulator. Now our simulator already run. Now we want to get a output, of P is equal to result dot. This one is our state vector representation or state vector output of our circuit. Here we are putting 0 0. For verifying this output, suppose already Siddhartha sir told you the entanglement circuit. Actually here I design an entanglement circuit. If we give 2 0 0, we can create a one bell state. This bell state will design our 0 0 and 1 1 state simultaneously. I think by showing this state vector simulation you can understand better. For better understanding, we need a chasm simulator. So just here, if we change our simulator as a chasm, and another thing is that before doing the chasm simulator, we have to put a measurement operator here. So I just put here some measurement operator. Now here we draw. If I put some measurement operator means that means we are doing a quantum operation within this quantum register. After completion this operation, we try to measure our quantum circuit. Okay. Just give me another. I want to execute from very first. This one is our quantum circuit. Now we are adding a backend as a chasm simulator. Same things. But here result will goes to the, here we have to, in case of state vector simulator we need a get state vector, but in case of chasm simulator we need a get counts. See here we are designing some entanglement circuit. Basically already we have seen in our discussed by the professor Siddhartha sir. He told what is actually entanglement state, and here we design a entanglement circuit and getting a output is like that. Here after doing that we will get as a output 0 and 0 0 and 1 1 because it is a 2 qubit operation. So here is a first qubit is 0 and second qubit is also 0 from the first year, and another one is 1 1. Basically we got this simultaneously 0 0 and 1 1. And what is the probability of existence of 0 0? There should be a almost 50% chance to getting 0 0 and 50% chance to 1 1. And another things, we can't divide this entanglement state, or we can break this entanglement state like superposition state. In case of superposition, we can separate, not divided. We can separate each and every qubit. But here, in case of entanglement circuit, we can't separate this two qubits. because they are very much maintain the correlation between these two qubit. And you see there is a probability to finding 00 is almost 50% and 11 is also 50%. But here we are doing just simulation. But if we want to do this here for simulation, we are writing so many code in Qiskit environment. But by using the just by using our quantum GUI based simulator, I'm showing how can we create. Already we know how can we enter into the create our account in IBM Q, and how can we use our quantum GUI based simulator. Here I want to design the same circuit quantum GUI based by using this GUI based simulator. First of all, we are taking a 2 qubit here, 1 and 2 qubit, and automatically it detects 2 classical bit. And first we need a Hadamard gate. We put here Hadamard gate. Next we need a control NOT gate. See, we are putting a control NOT gate. Here, see, here our quantum simulator gives you the output as a 00, 0 chance of 0 is 50% with probability, and 1 is a 50% probability. Now I put a measurement operation to here and as well as here. Now this one is I have simulate in a simulator only. But if I want to run this circuit, if I want to run this circuit in real quantum hardware, then we have to go to this button, setup and run button. And here IBM lists all its real hardware computer. See, this one is IBM from Santiago, and this is from IBM Athens, and this is one from Blame and Quito, and this one is a Melbourne. Actually, Professor Devashish De is really working in this environment, Melbourne environment, and he physically touch this machine. I say touch this machine and see that this one is a most popular quantum real quantum hardware machine exists in Melbourne. See, there is Antigua only 176 is program is running at that moment, and this one is Athens is 1700, but here see Melbourne is 6589 program is running at that moment, and it is provided a 15 qubit quantum computing environment, but they have more than 15 qubit, but only for the researcher and normal user they provide only 15 qubit. If you need more than 15 qubit, you have to book a slot for the IBM team with a negotiate with the IBM team. So here for running faster, I choose the minimum this one IBM Blame as my hardware. So I run now. I run on IBM Cube name, and see here it is showing job is queued in our system, and this one is still is in queue. When it will complete, it will show here this your job is completed. So let's wait for 3 minutes.
So that means your system is, program is running on the real IBM
Yes,
cloud.
yes. That means our
Real IBM
program is running in real quantum hardware at that moment. And see, I have already completed 1, 2, or 3 tasks in this real hardware, and now this one is a pending job, is pending still due to the job queue. We need this one is still 6 online, and now it is 5.
I think we can mention them that if anyone want to work in this cloud platform,
Yes, yes. Anyone
book
can
the,
work.
book the slot. We have to book the slot previously, so that they will give you the free slot, and you
Yes.
can faster operations. Yeah.
Definitely. And for running the quantum circuit in IBM Melbourne, it is very difficult. See that still it is a 6,589 operation in job queue. So if you put your job, you have to queue for 1 day also, more than 1 day.
So why it
And
is so popular? Can you just
because
explain?
due to its available qubit, this one is it is available by the 15 qubit, and all others it's just like a 5 qubit system, the 5 qubit system, all other system. And if you need more than 15 qubit, sir, you have to pre-book to Melbourne. You have to pre-book, and 15 qubit is readily available all the time. You see, gradually increases 6,590 old. It was previously 6,585. In Blame, this one is online in 2.
So if it is 15 qubit, it can perform the job very fast, right?
Yes, it can job first like 2 to the power 15 qubit at a time. It can work as a
Yes.
2 to the power 15 qubit at a time.
So that is a very important point for everyone. If it is 100 qubits or maybe more than that, 100 qubit is available nowadays. So these things can be done very fast, very, very fast. So especially for quantum cryptography, RSA and the popular algorithms we can break it within few seconds. That is the reason that post-quantum cryptography is very, very popular. I mean, going to be very popular. That all the conventional algorithms we can break anytime, right? Isn't it, Sudhandu?
Yes, yes, sir. Because see, main fundamental things for RSA algorithm is prime factorization. If we want to make a prime factorization in our classical machine for 6-digit prime factorization, it will take almost 15 years to
Yes,
compute this. But by using the IBM quantum computer and by using the source algorithm, we can see it can be done by within a few seconds, only a few seconds.
So that is the reason this quantum computer is so popular, and I have discussed also quantum search, Google search, whatever.
Yes.
So
And there is another popular things you are also mentioned already, but not in details. You are mentioning this Google search. That means this one they developed by using the quantum walk algorithm. Due to this seminar is, I think, for the basic students. That's why Devashish sir will not discuss quantum work in details, I think.
yeah, so it will take time, but for
it will take time. Basically, I want to show if execute in properly, then you can see what is the difference between execution in simulator and as well as execution in real hardware. When we execute in a real hardware, you can see we can get some error. We can get some error.
due to some garbage value also sometimes, right?
Yes, yes, yes. Basically, there's some scalability issue also exists. Like here, in this case, we go. If we use a 2-qubit system, that means there exists a 0, 0, 0, 1, 1, 0, and 1, 1 qubit probability at a time. There must be exist 0, 0, 0, 1, 1, 0, 1, 1. And but in this case, by using this entanglement, we are getting only that 0, 0 and 1, 1. This one is for the absolute case. But if we execute this in a real quantum hardware, we can see there may be a very little probability of 0, 1 as well as very little probability of 1, 0 due to the some error propagation. Basically, I want to show that by using this, yeah, but it takes too many time. Still, it is pending.
So Mithun sir, is it clear? Dr. Mithun Chakraborty, is it
Yes,
clear
yes.
that?
Sir, thank you very much for the knowledge that you shared. Really, the platform that you have shown to program, just to start with the topic that that was the today's discussion topic, and we got a lot of things collected today from all the sessions, and thank you very much, sir, for the session. Thank you very much for all the knowledge that we gathered. Devashish sir particularly, and along with Shudindu sir, the knowledge that you have shared.
Actually, Shudindu is doing currently the real, not the simulation, real quantum computing in the real quantum computer itself. So it is a very interesting to see, and we can our students can also do the login and they can try, but they need to know the linear algebra, and as Shudindu has mentioned, also they need to know about the basics of Python coding. And Python is very simple. It is even simpler than C language. We can access these things. So quantum computing is a reality. I think we have discussed many times with Professor Raman Kumar Jha sir also that we need to have this power of quantum computers in our laboratory, in our own computer. So we have to break the idea of quantum computer in your home. Quantum computer basically is a cloud-based access, because what the computer this Shudindu is running this program now, it is working at minus 273 degrees centigrade, minus 273. That means cryogenic, because the circuits are not possible to work in the room temperature. So we can do various applications like quantum machine learning, quantum neural network. I have shown you some biological applications, how our actin, our neurons can operate, even quantum neural network. These are the real applications. Even the banking sector, previous speaker Utpal sir, he has mentioned about how the banking sector can operate. And banking, I also worked with some banking in when I was working in a software company. So it takes a lot of time. But if you use the quantum computers, the message to the students who are present, we can do the huge amount of job in a fraction of a second. And that will save you time and energy, right? We can consider it on more various kinds of AI-based systems. So that is the beauty of this quantum computer. So it is the reality and it is possible. So all Shudindu has shown. So Shudindu, your job is complete. Please check.
No, sir. This still this one is in queue. Basically, if we execute in the late night, then it will take less time. At that moment, there are so many jams.
Crowdy. Now crowdy. A lot of people are actually working. Crowd is there.
Basically, from the US guys is execute at that moment because they are in the night and they are executing lot things at that moment. That's why there are so many queue in this.
Yes.
When
but still, we have shown how it is running. Yes, at least. Yes. But basically, if you want to do a full-fledged quantum computing workshop, it will take several days. But also at the same time, students have to be equipped with the knowledge of Python and everything. Then only it becomes we can develop the power of quantum computer in our even BTech project. Even some of the students are doing with Shudindu with the MTech projects, right? Isn't it? Yes. So I've seen it. So thank you.
Thank you, sir. Thank you very much, sir, Devashish sir, for sharing your precious time and the valuable knowledge that you have, along with Mr. Shudindu sir. Now with us, our Honorable VC sir. Sir, if you can say something or spread some words of wisdom on today's topic, sir.
Well, I don't think I can add more about it. I am a person from quantum mechanics, so I could appreciate the algebra and things like that. And having an experience of really getting onto, even though I had seen Qiskit and I have already an account with IBM, I was trying to do this, but seeing this done by Shudindu was not only fun, but a lot of already, I would say, an initial force has been applied that we will now get into it. So hopefully the group at AUJ will start learning more from all of you because you're into it already. We are just the beginners here. And with computer people with Python background also, we will have, I think, some time booked for understanding the basics before we really get into the circuit and related things. But this has been a real good exposure to a completely new field to those who are interested rather than those who do not know anything. So if you do not know anything, lot has to be first taken up, then this will get into your head. But it is nice to know that the whole world is working on this area and the computer is busy for so long. So which means the rush for it is already in, and that's the good thing to understand. And we hope that we gear up and take things further. Thank you very much to all these speakers.